esto funciona. Hello, may I have your attention, please? Now it's time to go outside and have a coffee plus drink, the welcome drink or welcome coffee. And at 9:30 we'll be back to start with the opening ceremony and the opening talk. Thank you.
Hola, hola. ¿Otra vez? Hola, buenas, ¿se me escucha? Hola, buenas, probando, probando. ¿Este también? Hola, buenas, probando, 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 probando. Hola, hola. Hola, hola. Hola, buenas, probando, probando. Hola, buenas, probando, probando.
Hola. Un poco. Hola, hola. Hello, hello, testing. Hello. Hello. Hostia, qué raro. O. Na, 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 na. Vale. Na, 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 na. ¿Cómo empieza? ¿Lo canto de verdad?
Tararealo, aunque sea, por
Vale.
favor.
Oh, na, 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 na. Na, 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 na. Na, 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 na. Na, 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 na. Na, 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 na. Na, 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 na. Na, 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 na. Na, 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 na. Na, 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 na. Na, 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 na. Sí. Aquí tú callas más fuerte, ¿no?
Hombre, claro.
Muchas gracias. Además, como se me ha escuchado raro, pues se va a subir. Además, como se me ha escuchado raro, se va a subir un poco.
Vale, pues. Perdona, este ordenador. ¿Tu nombre cuál es? ¿Cómo? ¿Cac? Sí, sí, claro. Puedo quitar este ordenador de aquí, ¿no? Sí. Exacto. Esa es la parte fácil, la que viene ahora. Castillo. ¿Quién Castillo? ¿Y Carlos? Es investigador de la Universidad de Coimbra. ¿Quieres en español? Sí, universidades. Te lo voy a poner en portugués, que lo único que hay en diferencia en portugués es esto. Porque si no, el Coimbra lleva acentos, ¿vale? Del castellano.
Y es esto. Si es en castellano, con acento.
Vale. Yo soy... ¿Ya comenzó ahora? Sí, sí, son las 9:30, yo creo que tengo que comenzar. Cuando tú me digas, Organizadores del Congreso, profesores y demás asistentes. Buenos días a todos y a todas. Bienvenidos a Sanlúcar. Bienvenidos a este Auditorio Municipal Manolo Sanlúcar. Es un honor para mí, como delegado de Cultura del Ayuntamiento de Sanlúcar, abrir este Congreso Europeo de Matemáticas, un evento de gran relevancia y prestigio que se celebrará hasta el próximo viernes en nuestra localidad. Este congreso reunirá a destacados matemáticos y académicos de todo el mundo para compartir conocimiento, discutir avances y explorar nuevas fronteras. En el campo de la matemática, Sanlúcar se convierte así en epicentro de un intercambio científico, reforzando su posición como un lugar de encuentro para la cultura y el conocimiento. Durante estos 5 días tendremos el privilegio de asistir a conferencias magistrales, talleres y paneles de discusión que abordarán temas que van desde la teoría de números hasta las aplicaciones más avanzadas en la inteligencia artificial y el análisis de datos. Este evento no solo será una gran oportunidad para los expertos en matemáticas, sino también para estudiantes y aficionados, quienes podrán participar y aprender de las mentes más brillantes del ámbito académico. En esta ocasión tan especial, queremos rendir un homenaje y reconocimiento a una figura excepcional de la matemática y un ilustre hijo de Sanlúcar Barrameda, Antonio Hugo de Omerique. Su trabajo y dedicación a las matemáticas han dejado una huella indeleble en este ámbito y su legado continúa a nuevas generaciones de matemáticos. Omerique fue un pionero en su tiempo, un investigador incansable y un educador apasionado. Su contribución al desarrollo de la matemática no solo ha sido de un gran valor académico, sino también una fuente de orgullo para Sanlúcar. Es un honor para nosotros poder recordar su legado y rendirle tributo durante este congreso. Quiero aprovechar esta oportunidad para expresar mi agradecimiento a la Universidad de Cádiz y a las demás entidades que han trabajado arduamente en la organización de este congreso. Su esfuerzo y dedicación han sido fundamentales para hacer posible este evento de gran envergadura. También agradezco a los ponentes y participantes su interés y compromiso en compartir su conocimiento y experiencia. Estoy seguro que las discusiones y colaboraciones que se generen durante estos días serán de gran beneficio para todos y todas. No quiero acabar mi intervención sin antes desearos a todos y todas una feliz estancia en Sanlúcar, una ciudad amable que ofrece numerosos atractivos y que acoge a los visitantes con los brazos abiertos. Muchas gracias. Muchas gracias, señor delegado, estimado Narciso. Well, I'm going to make my intervention in English, and then my colleague, Kenner Castillo from the University of Coimbra, will continue in Spanish. Well, first of all, I'd like to apologize for the technical issues. As you can see, this is an old church, a very old building with very good acoustics, but still it's not easy to set up a media system. So I'd like to apologize, but still we are kind of on time. So, well, after the apologies, I'd like to thank all of you for attending this conference in honor of the memory of Professor Jose Carlos Petronilo. This is a joint effort between the University of Coimbra, represented by my colleague Kenner Castillo, and by the University of Cádiz. And we are very happy to hold this conference here in this beautiful city, Sanlúcar de Barrameda, which is a very touristic, historical city. It's extremely famous for its wellness, gastronomy, wines, manzanilla, etc. So we hope that you have a great time here. not only scientific time, but also a personal time. And those of you who don't know each other very well, we hope you get to know each other better. That also not only ends up in scientific collaborations, but also in human relations. And finally, I would like to deeply thank the Sanlúcar de Barrameda City Hall for all the support that they provided us, logistic support, administrative support, political support, moral support also. And I guess I have nothing else to say. Thank you again, all of you, for being here, and welcome to this conference.
Buenos días. Paquito me pidió originalmente traducir al español su intervención. Yo soy muy malo en las traducciones. Por tanto, voy a hacer una traducción libre de la intervención. En primer lugar, quiero agradecer a todos por estar aquí. Estamos aquí para recordar, primero, no es el Congreso Europeo de Matemáticas, es una conferencia satélite del Congreso Europeo de Matemáticas. Y segundo, estamos aquí para homenajear no solo a un matemático excepcional, sino a una persona extremadamente noble y tímida, que realmente estaría muy feliz hoy de ver aquí a quienes fueron sus mejores amigos. Y también ver mucha gente que estimaba matemáticamente y personalmente mucho. Es un enorme placer estar aquí. No voy a extenderme ni voy a decir nada más, porque voy a respetar aquello que siempre decía Petronilo: digamos poco y hagamos mucho. Disfruten Sanlúcar, disfruten del Congreso. Y muchas gracias.
The conference is officially started. Okay. So we will have now our first talk.
Paquito, mi ordenador. Genial, cuando quieras, ¿no? Ah, él dice que tú y tú dices que él. Vale, vale.
Okay, let's start now with our first speaker, Renato Álvarez Nodaza. It's a big pleasure to introduce not only one of the most important friends of Petronilo, also a really good mathematician. But this talk, I'm assuming that is not related exactly with mathematics, it's not with the mathematician that was Petronilo and with the person. Renato.
Thank you for the introduction. I want to thank the organizers for just decided to organize a meeting and to dedicate to the memory of one of my best friends and outstanding mathematicians. So I will talk about his work and his life. I will start my talk, and I will finish my talk more or less like a Pink Floyd, very famous LP, Dark Side of the Moon. I mean, I will start with something, I will just make a round and just come back to the first. On Saturday 2021, I was just sitting in my room at home. I was talking with one of my oldest friends was Petronilo, and we was discussing what will be our next project, mathematical project. He was very happy. He was making a lot of jokes, uh, sarcastic jokes, essentially. He loved that. But he was very tired because in the last years he could not sleep so well. We always made a lot of jokes, say that about that. And we never, I mean, even I never knew that it could be happen that it was the last time we meet together, at least virtually. Okay, the first time when we meet, it was in Leganés. I was uh, making the PhD thesis with Professor Marcellan. He also, Marcellan tried to convince us to rent, say that a room for one of his students, and we didn't want to do it. And we argued a lot of stupid things like, what happens if this person smoke? What happens if this person, I don't know, is noisy? Somebody that knows Petronilo knows that this is the orthogonal to that, okay? But at the end, we did it, and he come. Okay, I remember exactly that was in the winter of 93, 94, maybe December or January, I don't remember exactly, and a little Ford Fiesta, red Ford Fiesta, arrived, and a young man, very thin and shy young man, go out from the car and presented himself. I am Jose Carlos Petronilo. And this was with him was his wife Celia and the brother of Celia, Fernando. They didn't want to go up because they need to come back to Sevilla, sorry, to Coimbra. It's a long trip. But Jose Carlos just stayed at home. I still remember that this day for dinner, we just asked him to join us, and Jose Carlos told us that he already have a dinner in a restaurant close to your house. And so we were very, very hungry with him, say that this is impossible, you cannot do that. Imagine, we didn't know to each other, and it was so embarrassing that after that, he never went out for eating in any place except with us. Uh, say that these first days, we never knew that we became very close friends. Even the families were very close friends. I mean, I and my wife, especially I, because I travel more to Coimbra, I just was a witness of how their kids, the two daughters, grow up. Okay. Oh, wait a moment. In this talk that is open this Congress, I will share with you a lot of remembering that I have. I mean, a lot, some of my rememberings, and also, of course, I will comment some of the mathematical, say that, results that he considered his most important results. Okay? Here is a photo in working at home. As you see, a lot of books over there, and this is the last photo of Petronilo. 1 hour later on, he had a stroke, and he just could not recover, and he died several days after that, surrounded by his family and his closest friends. Okay? So let me go. I will divide my talk more or less in the following. I will just talk about the works on classical and orthogonal polynomials, works on polynomial mappings, and some miscellaneous results. And for the end of the conference, I see that will be the most important part, because it will show you how this person, how good it was. You will be a little surprised. Okay? First, two words about his say that biographical data. He has been born in 65 in a little town Mira, beautiful beach, by the way, over there in the district of Coimbra. Okay, he decided to study mathematics. He have one of the highest mark, but he don't want to go to any medicine, which was very, how to say, uh, prestigious career over there, even lawyer, and he loved mathematics. People that know him can understand why. The main reason is he was a high passion about math. Okay. In fact, when he finished, he get the special award that is in the mathematics department of Coimbra for the student with the highest mark of his promotion. Okay. When he finished, he became assistant professor. It was the typical thing over there, and he started to work in his master thesis on polinomios ortogonales y funcionales semiclásicos, more or less the same in English. He finished in 93. He finished the bachelor in 89. In 93, he defended the master thesis, and in 97, he finished the PhD. I need some preliminaries in order that you understand what he did. He works essentially in orthogonal polynomial theory. For the orthogonal polynomials, you have a polynomials, Pn, okay, let P the space of all polynomials with a complex coefficient, and you say that they are orthogonal if, with respect to a functional, linear functional, if this product that you can see over there, okay, is 0 when the degrees are different and different from 0. If for a given functional the sequence of polynomials exists, then it is say that the functional is regular. Okay? A special case is when you have, for example, this representation, if you want the risk representation for the functional, but the classical one is when you get a continuous wave function, and then the orthogonality that you get is the classical one. Okay? In case that when you apply P to any positive functional, this is positive, the functional is said to be a definite positive functional. And this is one of the main area in which Jose Carlos was working during his whole life, okay? One of his first work was about characterization, but let me tell you a little history about polynomials in less than 1 minute. The first time that orthogonal polynomials appears in the history of mathematics was in the work by Legendre, in trying to understand how an spheroid is attracting, point masses. And he found an orthogonal polynomial sequence he called now Legendre polynomials that satisfy this relation that you can see over there, okay? They satisfy also a differential equation. The solution of a linear differential equation are these polynomials, okay? Because of the orthogonality, he also proved that they satisfy the three-term recurrent relation. All this work I will use during this talk, okay? Also, the orthogonality was with respect to a wave function, as I say, this rho, what is over here, and this rho is a solution of the first order differential equation named the Pearson equation, okay? Finally, they can be obtained explicitly expression for these polynomials using this formula, usually call it the Rodriguez formula, okay? The interesting thing is that that we call now classical orthogonal polynomials, that are polynomials that are related to the names of Hermite, Laguerre, Jacobi, and Bessel. They satisfy all these kind of properties. Interesting one is that their solution of this equation, their orthogonalities with respect to some wave function that satisfy these kind of things, and there's other ones that I will comment in a moment. Okay? To prove all these things, let me say that it's extremely complicated. okay? If you take a look, for example, of the paper of Wagner, who proved that the only polynomial orthogonal polynomial solution of the second order differential equation was this fourth thing, is very complicated to get. Even almost all. Um, I mean, so it was clear that somewhere at some moment it should be appear a theory that can help. And this theory, of course, was the functional analysis, okay, which is one of the topics of this conference. And in fact was Pascal Maroni, you can see him in that photo with Jose Carlos, the father of this theory. I will call that, it is called the algebraic theory of orthogonal polynomials, okay? Jose Carlos was, he was a fan, a big fan, it's the only I can say of the work of Maroni, and he really understood how it works. The main idea for the mathematician is that when you have the orthogonal, the polynomial space, I mean, the algebraic dual and the, say that, and the adjoint dual, if you want, are equivalent in some special, with some special topology, say that. And this allows you to use all the machinery of functional analysis on dual space and then get a lot of results in the normal space of polynomials. Okay? Let me talk about the first contribution of Jose Carlos on this topic that he considered his most important one from his first period of life. This was the classical orthogonal polynomials. Essentially, the definition is that you have a regular functional and then they satisfy a first order differential equation in the distributional equation. Okay, if you take a look to that, there's two immediate questions that appear. This equation has a non-trivial solution. Second, the functional, if you get the solution, is regular. I mean, it has some kind of orthogonal polynomial sequence. The answer to that was in a paper in 94 in integral transform and special functions. It's a very beautiful paper, okay? Summarizing, he found necessary and sufficient condition for this to happen, to answer yes to these two questions. And this is curious because if you get this differential equation, the point, I mean, the data that you have is these two polynomials, second degree, first degree polynomials, okay? Let's write in that way. And everything that you see is that the conditions only depends on the coefficient of these two polynomials, nothing else. Okay, you do not need to impose anything extra. Even from that, then you can find the coefficient of the three-term recurrent relation, which is the best way of generating the orthogonal polynomials, and also you can get a Rodriguez formula in the distributional sense. Was an amazing paper. Even say that he loved these results. Okay. You can just put everything together and then you can see that this theorem gives you exactly the necessary and sufficient condition to get the non-trivial solution, give a characterization of all classical functionals and therefore somehow classical polynomials. Okay, and the condition was beautiful. Okay, this is in red. It's very important because all the phi and c that you can get, you can multiply by obviously non-zero constant and you get the same solution. Okay? Everything depends only on these two things. Let me say one thing more to go further, was about characterization theorems. In fact, from his first paper was not this one, it was a previous paper with Branquinho and Marcellan about characterization, but he never liked that paper. He told me several times, especially at the end of his life, that he don't like so much that paper. And I understand why. He told me, in fact, in that paper, it is assuming that the functional was regular. And of course, if you assume that, it could be that the functional was not regular, so you are assuming something that is doesn't exist. Okay? But secondly, he realized that Maroni itself had been announced this characterization in a paper in 91 it's a typical scene in the French school that they announce, and by the way, the French school, and I think also that was the Soviet, now Russian probably school, they announced the results in a little letter, say that, and after that, they wrote a big paper, say that, on that things. The Maroni's paper arrived more or less at the same time at the, say that, this paper in 93. But the other one, even Maroni was unable to prove that the functional was regular. So Jose Carlos was very proud that he did, okay? I will just mention some of the characterization, but now I will move 30 years, as you can see. This appeared in 23 in the result of mathematics very recently. For example, if you have a classical orthogonal polynomials, the name of Jacobi and so on that I told you, then this is the only one that satisfies this Pearson equation, distributional equation. By the way, this was Maroni's characterization. The second one is, for example, the Al-Salan-Chihara characterization that claim that the only sequence of orthogonal polynomials that satisfy this differential difference equation was the classical orthogonal polynomial. The Ham is related that the only orthogonal polynomial sequence that satisfy that their derivatives are also orthogonal polynomial sequence are the classical one. The C4, which by the way, several times for key equal to 1, was attributed to Marcellan, Branquinho, and Petronillo, but this was wrong because in the 1940, Hieronymus have proved this in a beautiful paper that unfortunately only it is in Russian, so a lot of people miss. But I mean, you can find, you can find in the internet. The boxes that I told you about the differential equation and also the Rodriguez. This C4 for arbitrary key is a contribution by Jose Carlos with Kenyer in that paper. Okay? Let me say that when you take a look to the proof of this theorem, the proof is hard, okay? But if you compare with the proof, original proof for C1, C2, say that, C3, C5, or C7, you realize how powerful was the algebraic theory invented by Maroni and developed in a very beautiful way in the works of Petronillo, okay? Now I will move to his second very important contribution was about orthogonal polynomial mappings. An example, a classical example, if you have the sequence of L and H, Laguerre and Hermite polynomials, and you can see that the Hermite polynomial can be related by this Laguerre polynomial just by a chain of variables, okay? And so Jose Carlos, in his thesis, he solved this kind of problem when you have two special cases. But I will just discuss the general case that he also solved it later on. Suppose that you have a monic orthogonal polynomial sequence, fix a key less or equal than 2, and suppose that you have another orthogonal polynomial sequence. And the question is if you can find some kind of relation like this. The Pn with the proper degrees is equal to the Qn evaluated in some polynomial, that is the polynomial mapping, multiplied by some polynomials in case you need the degrees works, okay? The complete solution of that problem was done in a paper of 34 pages, which is very hard. The proofs are elegant, but yes, it's quite hard. It's a lot of things to solve. That he did with his first PhD student, De Jesus. It was published in Journal of Approximation Theory in 2010. He gets a full characterization of that problem, but also he recovered all previous results. This is one of the best contributions of Jose Carlos in the theory. He was very proud about that. Okay, as I told, he used that. He obtained the result for key equal 2 and 3 in his PhD thesis in 97. But several times he told me that he was very unhappy because for the case key is equal to 2, say that the proof was not elegant from his point of view. But he found a way to solve the problem for key is equal to 3, and this gives him the key for solving the full, the complete problem, okay? And he was very unhappy because the two papers he wrote in k is equal to 3 because of the suggestion of his advisor was sent to a journal that nobody knows. And everything was based on these two. He was very unhappy, uncomfortable with that, but I should say that Jose Carlos was some kind of person so shy that he could not refuse when they get this kind of offer. Okay, that is the paper over there is this one, okay? But in honor of the truth, I must to say that 5 years before, he solved not that problem, but using almost the same theory with not the full characterization, he just able to apply this in a beautiful area of linear algebra is the so-called the Cat-Oplis matrix. In fact, finding inverse and eigenvalues and eigenfunction. I will take a little history that happened with me and him, and that say too much not about him and about the academic world we are living over now. For example, when I came in 93 and started working in my PhD, I get the suggestion from my advisor to find an application of the Kral polynomials. I was shocked. The Kral polynomials say that are polynomials that are say that perturbation of the normal polynomial. Suppose that you have a sequence of polynomials with respect to u, okay, and then you add to the functional some kind of, say that there are functionals, okay? And at this time in the 90s was a lot of active area of research in orthogonal polynomials, and there he was interesting to find. I came from physics, so I suppose that I can find a physical theory. But for me it was a shock because I came from a school, the Russian school, now at that time was the Soviet school, and they taught me in a different way. You have a problem to solve, a physical problem, whatever you want, and then you find a way to solve it. If you need to invent the mathematics, you invent the mathematics. So the idea was not you have an invented theory, invented in the sense you found a theory, and then with this theory try to find an application. But I later understand that it's a question of selling. I was living in a, say that they call Communist Party was nothing to sell, you know? And the science, in fact, was not something that you never will say. It was forbidden, okay? Okay. What happened? After in 94, after I think that 2 times he came and lived with us, always we have a lot of discussion because we didn't want to get money from him. He insisted, but at the end, we became more or less a little friends. The friendship was started, and since all the time he was eating with us, even go to the university with us, and so on, we start talking about what he's doing, what I'm doing, okay? And so in 94, he invited us to to visit him and his family in Portugal, and we spent a beautiful summer in 94. This is Jose Carlos with his little daughter, Sara, okay? It was almost 3 years old, and there we are just sitting, eating with her father, Joan, and her mother, Elena. Sara is always sitting up there, as you see. Okay, we start talking and talking and talking, and what happened? On 95 or something like that, he was sitting and tell me and explain me what he's doing with this polynomial mapping. And I don't remember how I arrived to a paper that is related with the so-called chain model. The idea is the following. Suppose that you have a quantum mechanics system, okay, and you need to find the solution of the Schrodinger equation, okay? Usually you cannot solve the Schrodinger equation analytically. I mean, the real one. So what the physics did is the following. You get an expansion on some kind of, say that complete basis in L2, then you expand this, and you get corresponding products, and then you change the differential equation somehow, or if you want this equation to a system of equation. When you get the system of the equation, it looks like that. Everything is okay. You put in a computer. Oh, but if you put in a computer and this n, capital N, is too big, just the computer just blow up. You cannot solve. Okay? So there you need to find models. One of the simplest models was the so-called chain model. The chain model, the idea is there is a way of changing this huge, with non-zero matrix to a tridiagonal matrix. The tridiagonal matrices are beautiful, and since there's a tridiagonal matrix, there is direct connection with the theory of orthogonal polynomials. And from this reason, Jose Carlos started working that. Even the periodic. For example, for key is equal to 2, he completely solved the problem of finding the eigenvalue problem. He found that the eigenvalues of this matrix that I show you are essentially the solution at the zeros of some polynomials is n that is given that way. And this p is nothing else than the Chebyshev polynomial, okay? And you need to find the solution of this. Imagine that you have a matrix of, 1 million entrants, dimension 1 million by 1 million. Nobody can solve that. But since it's a periodic, the only thing that you need to do is to solve this little second order equation, algebraic equation that is very easy to solve. Okay? So most important thing that we found, or he found, is that when you try to find the orthogonality measure, if you want the functional or the distributional function, what we see is that you have a continuous part and you have a delta. And when I saw that, I said, oh, Jose Carlos, this is a Kral type polynomial. This was the thing that I asked for to take a look. So we found an example of application that we never expected. We decided just to work more on that, and after some time, we wrote a little paper in the process. This was in the 95, in 96, we become closer and closer. This is a photo. We went together for a summer course in approximation theory in Vico Equense in the Naples Gulf Stream. It's amazing. It was in a ship, and there this was a discussion that we have with some wine, as you can see, just the day before I defend my PhD thesis in June 96. Okay? I will finish this part with a little example of what this was so interesting. If you get a real Hamiltonian like this one, this is a way that you can describe, for example, a ring of coupled oscillators. By the way, non-linear oscillators. If you have the ring, you have a periodic matrix. But if you have a chain of oscillators that also appears in a lot of applications, then you have not a periodic matrix. That we found is that you have, instead of tridiagonal matrix, you need to add at the beginning and at the end some kind of perturbation. So I was thinking how we can solve that. Of course, the only way that I can solve that is to come to Coimbra and ask Jose Carlos what we can do with that, because he knows everything about these kind of things. And we decided just to solve that problem. The first thing that we did was to discuss what is the relation between the zeros of this perturbed matrix when this mu and lambda is zero, okay, and the one when you have these two parameters that were positive in general. Okay. If you know how they interlay, you can get more or less properties. The second one is how close they are, because it say that in applied math or applied physics, applied, science, you not only need the theory, you need to get the numbers, okay? And so mathematicians love to do everything analytically, if you can. So if I know how to solve one of the problems, in fact, I know how to solve this exactly, okay, then I can know how to solve approximately the other. How close they are? Okay, the first theorem that I just showed you the idea was, okay, for this matrix, all the eigenvalues are just inside some intervals that are the inverse of the mapping of the polynomial pk, though that polynomial that appeared in the definition or in the problem of the polynomial mapping that I just showed, 10 minutes ago. A key point is these delta polynomials that he found very very useful, and he was an idea that he found in papers of Ismail and Charris, okay? And he found that everything, well, we found that everything is inside this interval except key minus 1 point that are separating this interval and that are exactly the key roots of these polynomials, okay? That is the good picture. You have the polynomial mappings over there. You have your interval, and you construct these three. Everything lies here, 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 and maybe you can have these two. That you have these 2 points or not depends only on the parameter of the matrix. At that time, I must to say that this was working, we were working in a European project that Luis Cardoso, who is sitting over there, and me, convinced him to do it because we needed a partner in Spain and a partner in Portugal. He didn't want to go, but at the end, he decided just to run for that project, and we got it, and we worked a lot on this, on these things. Also, Nurka, that was sitting over there, was working with us and helped with the numerical simulation that Jose Carlos don't want to hear any words about that, and for me, it was very complicated, okay? Let me prove one thing at the conference. The idea is the following. We went to the office of Jose Carlos and started thinking on a particular example. After get some idea or some hypothesis, we just went. It's not moving anymore. To a larger blackboard because you see we have not sufficient space. I start discussing, and at the end we get the results. So time for beer. But this time the time for beer was because you realize that somebody took the other picture, and it was Luis Cardoso that don't want to that we continue working and just take us for a beer. Okay, that is a joke, obviously. That is the result of the how close the eigen values were. Okay, just take a look to the last one if you want. At the end, we get this is the perturbed matrix. This is the one that we can find essentially in a very easy way the solution. Of course, for key is too big, no, but for 2 and 3 you can get analytically if you want. As you see, as n is bigger and bigger, you can get there closer and closer, and so you can almost, for the application, use the not perturbed matrix, and everything goes well. I need to say that we found other interesting things, and we make a lot of numerical experiments thanks to the program that Nurka grow, and we found very curious, say that, phenomena. And at the end, in 2000, we published some paper in 93, in 95, something like that, but this takes a lot of time, and only in 2012. We get a very nice, say that, time at this time. And to finish that, I must say a little history. I remember the first time when I come with the proof of this kind of bones, this charge bone, I used the regular perturbation theory, which is very typical theory in the mathematical, applied mathematics. And when he saw that, he refused. Say that it is very applied. I cannot do that. I can accept that the result is okay. I show the simulation and say, no. And then he starts thinking, and at the end, he arrived to the beautiful proof using elementary classical analysis. That is the way always he was thinking. To get beautiful proof in the sense, say that, or Hardy or Dirac, that say that it's a proof or the theory is not beautiful, that is not a good theory. Okay? I move forward. The next beautiful contribution of Jose Carlos was related also with the algebraic theory. I briefly comment some of the results. It is even very old thing. The first problem related with that was Hieronymus in the 1940. Suppose that you have a polynomial, orthogonal polynomial sequence Pn and another one Qn, okay? And there is a linear relation between that. This symbol means the derivative. Could be the classical derivative could be discrete derivatives, Q derivatives, whatever you want. In this paper, in this one, it is a classical derivative, okay? And so the question is to find a relation between, if there is any relation between the functional with respect to which Pn are orthogonal and the one that the Qn are orthogonal. I mean, U is the functional with respect to which Pn are orthogonal and V to Qn, then there isn't a relation of that. He was always interested in finding this kind of problem. If you get this n, big N, equal to 0, okay, this m equal to 0, and the other one here equal to 1, and this m equal to 1, no, to 1, not to 2, then you get the Hieronymus problem, okay? And that was one of the characterizations that I told you that they, and this is somehow a generalization. He solved that in a paper, this is Hieronymus. Let me check, yes. He solved that first for very particular case in a very short paper in Journal of Mathematical Analysis. And the general case he solved with De Jesus, his student, in 2008. And he used the Maroni algebraic theory. I guess that without that you cannot solve that kind of problems, okay? But the idea was so good that he just invented, or he generalized this, and he introduced the concept of M-coherent pairs in a paper with De Jesus, okay? The idea is that you have these kind of relations, and the N and N, M and N as the number of say that, of summand that you have here and here, okay? So they prove that when M is equal to key, this is not the one that I wanted to show. Okay, in any case, I have no, I will just, they found the theory, how they're related, but also in a special case, then they prove that the functional are semi-classical. If this is semi-classical, then there was already the theory completely developed by Maroni about semi-classical polynomials. So he can use it, and you get all the problem solved. One interesting connection was that this is related, this kind of expression is related with the so-called Sobolev orthogonal polynomials. If you know how to solve this linear relation problem, say that, then you have a way of efficiently found the Sobolev orthogonal polynomials that are very interesting in numerical analysis. And the problem that Jose Carlos solved, in fact, and the connection he found with the Sobolev orthogonal polynomial was a non-trivial generalization of an already classical paper by Serles and collaborators in 91 that appeared in Journal of Approximation Theory. Okay? Finally, let me say that he generalized that. Here is the N and key that appears. Also to the Q derivative and this kind of stuff, okay? But at that time, it was around 2016, it was completely exhausted. I remember in 2016, me and my wife asked us for a sabbatical to go to Germany. I got it, and she didn't got it, so we didn't go to any place. But I traveled a little, and I come to visit one time, and of course, he cannot say no because it was me, but he told me that he cannot work. He said, I don't need to work. We can go and take a restaurant, take a walk, talk about life or kids, whatever we want. And he told me he cannot survive anymore. He's very tired. And I will try to explain you, but because in our life, we will have good moments and bad moments. And I think that it's very important to know this also in his life. He was appointed as a associate professor in 2005. And after that, he need to pay for that. Say that, okay? There is no written rules in Coimbra that when you get associate professor, you need to spend some time with bureaucracy. And he was a member of the Bologna Commission. This means he need to understand how to transform the Portuguese system to the new European system. He did so well that the rector take him to all the meetings in Lisboa. In 2007, he was elected a member of Scientific Commission. He got a lot of work over there until he died. He was a vice president of the department from 2006 2009. When he seen that everything is okay, he was the vice president, also director of the department from 2013-17. And at this time, he was already, exhausted. Okay? I several times told him, you need to figure out how to just relieve the stress, because you cannot live with that stress. I tried to convince just to run, to go to swimming, whatever. Even when I went to him during that period of 3 or 4 years, we take a walk and so on. I used to run, but okay. At the end of his life, somebody convinced him. It was Kenya. Kenya appears in Coimbra around, I think that in the end in 2015, I started working with him, and he convinced at the end just to go some sport. And I was very happy, but maybe it was too late, I don't know. Okay? In 2018, he decided to apply for aggregation, for habilitation. At the end, he was thinking several times, as usual, but at the end, he decides to go, okay? And he got it. After that, when he finished all these things, of this bureaucratic thing, he has been reborn from the mathematical point of view. I think that probably Kenny helped a lot, because it's a young postdoc arrived with strengths, he wanted to work, and he took Jose Carlos, and at the end, he started working. And I was just told very little, because I have not much time. What was one of his last contribution that, by the way, he sing was his better contribution, was the idea of Kenner was try to put together the theory of Maroni and the theory of Nikiforov Uvarov of orthogonal polynomials. Jose Carlos knew perfectly the first one. The second one he knew more or less, because I explained several times. I was educated on that school and with Nikiforov. And the idea is you have the differential equation, you use, say that, an approximation scheme, for example, in uniform lattice, and then you transform this into the difference equation and work with that. Numerically, you can do this in a very easy way. But what Nikiforov and Uvarov really did is they realized that you can do in any lattice, nonlinear lattice. In fact, they show that it's sufficient to use this kind of lattice. This is very interesting, because the first lattice that you see with this Q over there, this is the typical lattice for the Askey-Wilson polynomial. The second one is for the Wilson polynomials or Raka polynomials. All the theories you can find in the book of Nikiforov and Uvarov. The first one is the Russian edition of the special function of mathematical physics. The second one was the English translation of the discrete case, say that he grow, they grow. At that time, they invite me to work with, he invited me to work with his new team, which was Kenyer and the new student that they have is sitting over there, Dieudonné, and we solved the problem, the characterization problem of classical functional, but for the Ham operator, okay? In 1907, I went again there. He invited me to give a talk and to discuss for the next project. He was quite happy, work a lot. You can see the blackboard is full of, we get dinner with some friends. In there you can see one of the oldest full professor, catedrático in Coimbra. Jose Victoria, that was a close friend of him. It is important to mention. He was happy. He took me to some excursion. Let's go to Porto with Celia, and the other one was Figueira da Foz to see the sea, to talk. We talk a lot. We work a lot, but especially we talk a lot. Okay? And start working in our thing. I mean, that is the main theorem that they prove. At the same time, with Kenyer and Dieudonné, after a lot of work, he showed me the paper before sending to any place. It was an amazing paper when they say that they did what he started in 93, and he classified all the functional that are regular but on lattices. And he recovered the ASCII Wilson, all these kind of things. It was a beautiful, I get some envy. Oh, he really did a beautiful work, and I was very happy. He was also very happy. But at that time, already he have a big problem with sleeping. I remember a lot of discussion that we have together with Celia, even Luis Cardoso tried to explain because he have also some little problem with sleeping. Okay? I am just coming to the end of my talk. So the papers appeared in 2002 after being rejected in two journals, in Journal of in a country's approximation and the proceedings, and he was very upset because he have a lot of rejection with unfair referee reports. And this has also history with a person sitting over here, because this was also rejected in Journal of Mathematical Analysis and Applications. And I know that after Jose Carlos' death, they got, Kenner showed me a report was awful, and then he just sent an email to Aaron, Richard and Aaron, this is over there, and Aaron realized that he was very unfair, and just asked the editor just to sing about what they are doing, and finally it was accepted, but Jose Carlos could not see his most important work just published because he died before. Okay, to finishing, I mean, it will be appear now a book. The history of the book is very complicated. I will not spend 5 minutes on that, in which everything, all this algebraic theory is put in a beautiful way. It was an idea of working with by Kenner and by Pascal Maroni with Kenner, but Kenner say that Jose Carlos should be there, and at the end, only Jose Carlos and Kenner did, and will be appear right now. It's an amazing book. It's a real gem. Okay, I mean, we start just the last time when I was in 1920. I come to Coimbra for the last time. I never knew that was my last time up to now. We again gone to Jose Victoria, to some places. We were at home. You can see over Kenya the Jose Carlos' daughter Inez that will become, I think that on Wednesday probably. He was very happy. You can see his face. We all were very happy because he's not the sad person that I remember from 2016. But then there is something that happened. And just to finish, I must to say two things. The first, I cannot cover all his work. I cannot cover the work he did with his very good friend Luis. Okay, we were tried every time to get a work together, but it was impossible for several reasons. Okay, in fact, this photo we are three over there was in a cool day when we finished to prove that theorem on matrices, and then went to beer. Okay, just to finish this talk, I would like to ask my kids to come to the stage, because I have a little surprise, and I will finish this talk in 5 minutes, please. Let me just finish with, as I promised, in the same way I began. Okay. I only knew that Jose Carlos was in the hospital the day he died. It was some kind of strange thing that happened, but the next day was a Saturday, and this Saturday 2027, around 2 p.m., my phone started just ringing all the time. So several people just, the camera just need go to them, please. Some of the people called me, but one of them was especially sad. I mean, just Victoria just phoned and asked me if I know the news. I said that I know the bad news. And he started just saying, the only word that he could say, es tan triste, Renato. It's so sad. All the time I'm finished. Then, when I come home, my wife asked, we were in a park with a relative that came from Madrid to visit us, okay? And when they arrived, we was all the time just drinking a beer. Where there was summer, August in Sevilla. Some people can, if you don't know, I can show you, it's hell, okay, over there. In the afternoon, my wife asked, what is happening with Jose Carlos? I say, oh, it happened that, I say, Sofia is asking. I tried that nobody here. I left, well, I was in a park, I was far away, but Sofia is here. And then on Sunday, I just, we have a special lunch. Then I opened my best Porto wine, a vintage, but almost sure that was him or Luis, and then explain the situation and so on. But then few days later, I came to the Sophia's and she told me, what are you doing, Sophia? And she said, I am writing a song. What I seen that day, can explain better.
Hi everyone, we are Sofia and Renato, and we are going to perform a song that we wrote in the memory of Jose Carlos. We wrote it some time ago, so it's a simple song. It's a bit childish, I think, but I don't know, we kind of like it, and well, it's in the memory of a truly wonderful person. So I hope you like it.
Oh, my friend, you've gone away. You've taken that trip and I won't see you again. But it doesn't matter, I still have you here inside of me. I knew you were going to go someday, though I wasn't expecting it for it to be so soon. I thought we had time left, but I remember you, I remember you as the person who made me smile, as the person who taught me that 2 + 2 = 3, a person who I aspire to be. Oh, my friend, you had a hard life, and it's difficult to realize I won't hear you again. But it's alright. Oh, my friend, you've gone away, but in my mind I remember you as the great person you were. my friend, I'll think of you again. Doesn't matter how soon you left. What matters is how long I'll remember you, and I promise I'll remember you. You tried so hard. What a brilliant mind. I won't let the memory of you fade away. I'll remember. I'll remember. I'll remember you, my friend.
That's all. See here or go there, whatever you want.
Yeah, I mean, this I understand.
Yes, it's a classical.
Sorry. Like to thank Renato for his beautiful and heartbreaking talk, and also his children for the beautiful song. And now our next speaker, I am very happy to be the chairman of the next talk. Our next speaker is Professor Richard Aaron. No, no, it's okay. the, just some technical issues.
There is more than that.
Sí, no toques los de abajo. Cuidado con los de abajo.
Pero solamente eso.
Sí, y el entero. Arriba.
Sí, sí, ya está.
Eso es el misterio de la informática.
Okay, thank you. Well, like I was saying, this is a very special moment for me. I'm so happy to be the chairman of this of next talk, because our next speaker, Richard Aaron, he was my PhD advisor at Kent State. I did the PhD with him, Kent State, on some three nonlinear problems. And so I really, that was when I started growing as a mathematician. I really have very good memories from my stay there in Kent State. And so I'm really extremely and deeply thankful to him for all he taught me, like all the mathematics I know, like everything I learned from him. So it's really a pleasure to introduce him now. So he's going to be speaking about some problems of possible. I'm sure there will be a lot of interest. Thank you very much.
Well, thank you. Can you hear me? Thank Thank you. Well, it's really it's an honor. It's an honor to be here. I can you hear me? Can you hear me now? Now can you hear me? Okay. If it gets too boring, okay. So I mean, the talk. At the moment, the key word is possible. So let me explain what I'm talking about. Okay, so I'm going to give two rather, I mean, obviously short presentations. And let me make a graph. Time is 0 to 30, but it won't be 30, but it'll be less than 30, but 0 to 30. And this is interest. Your interest. Okay? Now, what I hope is, and as I say, it's going to be two possible parts. So maybe here, and I hope we begin like this. And then I say the first part is going to be a little bit more technical. The second is not at all. So I hope that the second part, it will be like this. That's my hope. But sometimes I'm disappointed. So it could be like this. And at the end, you will all hate me. So, well, let's see. So, okay, and as I say, the first part is going to be more, slightly more technical, but not too much. Each part has two definitions, so here we go. So the two definitions are about what we call WMP, where to go, WMP, and CPP. So what's the WMP? So a pair XY, mono spaces, has the weak maximizing property, means the following. You take any operator from X to Y, and suppose that you can have a sequence Xn in the ball, such that T of Xn approaches the norm of T, and moreover, Xn itself does not converge weakly to 0. And then if that happens, then T attains the norm. And whenever that occurs, we have this weak maximizing property. Here's another property which doesn't seem to be related. It's the compact perturbation property, CPP. And this is much easier to understand. If I have two operators, T, K from X to Y, K is compact. And suppose that we have this inequality. Then T plus K attains the norm. So in other words, if the perturbation by compact increases the norm, then you have attaining the norm. Let's do an example. So the example is the scalar field. Let's T be 0. Let's let K be any continuous linear form. So let's say that we have CPP, compact perturbation property. So what does that mean? T is 0, so there instead of T is 0. And K is some linear form, and it implies that K attains the norm. So any linear form attains the norm. So what it means is we have reflexes. Now, okay, I mean, and I don't remember what year, but not so many years ago, Domingo Garcia, Daniel Pellegrino, and Eduardo Teixeira. The two are from Brazil. Domingo's from Valencia, and I. And what we showed was that the weak maximizing property implies the compact perturbation property. So I'll just go. So the weak maximizing property is this slightly technical thing, and the compact perturbation property. Now, what I'll do is, I don't know about the time, but what I'll do, the smartest thing to do is this. I'll recall what a famous American president from the 1960s and 1970s said. I won't give you the proof, you just have to trust me. So let me go very quickly, and now, well, yeah, let me just see. The summary, WMP implies, I mean, and you can see, that's really the proof, so it's not very long. WMP implies compact perturbation property, that's what we showed. If y equals k, CPP, compact perturbation implies reflexive. That was just a remark we made before. So, okay. By the way, suppose X is reflexive. If X is reflexive, automatically you have, and so if X is reflexive and Y is the scalars, then automatically you have weak maximizing property. The reason is, you take an operator which is a linear, now it's an operator into K, into scalars, so it's a linear form. And it attains the norm because it's reflexive. Therefore, it attains the norm at some non-zero vector. Take that vector and repeat it infinitely often. That's a sequence which works, it's non-zero, it attains the norm there. Okay. Now, here are questions which we wondered about, and there are many questions still around. This is fairly recent material. So we wondered about the converse, whether reflexivity implies weak maximizing property in general. And in 2021, Sheldon Dantas Mingujong from Korea and Gonzalo Martinez from, I think, Granada, I'm not sure, show that for some non-reflexive monospace pair, CPP does not imply weak maximizing property. So even what we wanted is by no means true. So, okay. Then later, it was observed a few years ago, there are no examples of reflexive spaces which give counterexamples. They're still open. And they also show, though, take a reflexive monospace, you can find another reflexive monospace Y, and you can find two operators, T and R. T is an operator, and Y and R is rank 1, so it's as simple as it can be, which have the following property. The norm of T is less than the norm of T plus R, so we have this perturbation by rank 1 operator, but T plus R is not norm of T. So there are many things which are somehow delicate, subtle, and well, I hope at this point now the second part of the talk. So, and again, this is, this began in the 1990s or 1990s. But let me begin with two definitions. So X is an infinite dimensional vector space, and this is somehow vague. P is a property, and the property is something that some vectors in the vector space may have it, and some vectors may not have it. And S of P is those which do have the property. So it's a subset, maybe empty, but not so interesting, but it's a subset of the space of this Banach space, infinite dimensional vector space. And P is said to be linearable if this set contains an infinite dimensional subspace. And I should say S of P, we add 0 to it, the 0 vector, because sometimes, well, just to avoid trivialities. And it's called, P is called spaceable. I should say that if you use any kind of editor when you're typing, spaceable occurs in red because the word doesn't exist, except that's how life is, and nor does lineable, but in any case, if, moreover, S of P contains a closed infinite dimensional space. Okay, these concepts were known to Vladimir Gurary in the 90s, and they were extended quite a bit by many mathematicians, many of them Spanish mathematicians, Paquito, Manuel Maestre, Juan Seoane, and many others, and other, not only Spanish people, but. Okay, let me give you some historic examples. So, the property, I mean, in each case, I think it's obvious what the property P, where to go, P is. So here, in the first example, the property is nowhere differentiable. Okay. So look at the collection of continuous functions in the closed interval 0, 1. And I mean, it's spaceable. Namely, you can find a closed infinite dimensional subspace. And in fact, okay, this was a result of Vladimir von Gurary and Kadets. The Kadets, the father, not the present nowadays son. And it was improved substantially by Luis Rodriguez Piazza from Sevilla. Okay, so, and this somehow is typical, this example is somehow typical of what's going on. Namely, the function, the property is an unpleasant one, let's say, not very nice. How about the corresponding nice property? Namely, the set of everywhere differentiable functions. What can you say about that? Well, it's lineable, it's a vector space. You can take two everywhere differentiable functions and add them, and everything is fine. It contains the polynomials, so it's an infinite dimensional space. But in fact, Gurary showed it is not spaceable. There are no closed infinite dimensional spaces. And what I want to do is just give examples. So the rest of the talk is really going to be just some examples. Okay, so E is for everywhere surjective. So look, these are functions from R to R, so from the reals to the reals, such that, no, I mean, I have the board, so I'll use it. You take any interval, there's a function such that on any interval, the range is infinite. Any interval. So take a smaller interval, there. So it's, I would say, surprising, at least at first glance, that such a function exists. And I can tell you I know two proofs, and one is surprisingly, well, it's direct. It's not, it doesn't use any machinery at all, anyway. And what's surprising is that it is, it contains a vector space of enormous cardinality. So, maybe not intuitive, but that's how life is sometimes. Okay, now this is not hard to explain, but there are too many indices, so I'll do it very quickly. We're going to look at three numbers. So it's it's D and K. D is going to stand for degree of polynomial, and K is going to describe size, number of dimensions. And given D and K, there is another integer m, such that the following occurs. Take any polynomial in m variables, complex polynomial in m variables, then it will be a constant on the polynomial is of degree d or less. It will be constant on a subspace of dimension k. Okay, now this is a result actually that was solved the problem in the Scottish book at the end, more or less, of the 1990s. And just to give you an idea, not of any particular interest, but if you have, what it shows is that if you have a polynomial in quadratic, a degree 2 polynomial in 25 variables is constant on the subspace of degree 11. What you do with that information, I don't know, but it's an example. Okay, and this can be, in fact, originally it's a proof about an infinite dimensional space. And there are some positive and negative results about zeros of polynomials, and let me just skip them, except to say that there's a paper I have with Chris Boyd, Ray Ryan from Ireland, and Ignacio Zalduendo from Buenos Aires. And we're very proud. The paper appeared in the Journal of Approximation Theory, I think, I'm not sure. And we're very proud of the title of the paper. The title of the paper is Zeros of Polynomials, the Real Story. And why the real story is because we're interested in real. Now, if you think about it, it's completely trivial. You can't have the results in general. Take the polynomial summation xn squared. So, okay, there's nothing, it's going to be zero on where it's going to be zero is nowhere, except the origin. But for cubics, it's already interesting. And I won't go into that. Okay, so here are some strange examples of functions. So the property is that it's everywhere differentiable, but nowhere monotone. So again, I have the blackboard behind me, but I can't draw it anyway. So, okay, there is such a function. Here's a result of Chiselsky and Juan Celani. And from 5 years ago, there's a function from R to R such that for any large subset of S of R, the function restricted to S is not continuous. Now, so the function discontinuous on S. A little over 100 years ago, it was shown by Bloomberg that no matter what function you have from R to R, there's a function there's a set which is dense and on which the function is continuous. So, okay. Here's a result of Mazurkiewicz from the 1930s. Again, not somehow anti-intuitive, I think. Namely, there's a function from 0, 1, a continuous function on the closed interval, which takes sets of measure 0 to sets of measure 0. But if you translate the function by anything which is not 0, it no longer does that. So again, these are strange, anti-intuitive examples. Here's the theorem. each of these properties not only exists, I mean, your intuition, my intuition is that you look at that and there should be no such function at all. And in fact, there's an infinite dimensional subspace of such functions. So let me give, and I'm almost at the end, maybe of your patience, but I'm also at the end of my time, and it's the following. Let me give examples where lineability fails. So there's a result of Gurari and Quarta from 2004. Quarta was actually a very brilliant mathematician who saw the future and now is making a lot of money in banking. But in any case, he look at the real valued continuous functions on 0, 1, which attain the maximum, not the supremum, the maximum at one point and only one point. Okay? Now, this set is a density delta. It's very easy. The set of such functions. To this, you can see I have to add the zero function because the zero function does not attain its maximum at only one point. So it's a density delta, but any vector space contained in it has dimension at most 1. So here's another example. This is maybe the most famous example in recent times by a Czech mathematician named Martin Remutil from 2017. NA, so X is a Banach space. NA of X stands for norm-attaining functionals. So NA of X are the phi in X star such that phi attains its norm. And the question is how, well, we know from the theorem of Bishop-Phelps, let's see if I wrote that. Yeah, if X is reflexive, then of course everything attains its norm. So NA of X is exactly all of X star. The Bishop-Phelps theorem says that NA of X is always a dense set in X star. And Remutil's result is you can renorm C0, the null sequences, to get that it does not contain a two-dimensional subspace. So again, lineability fails spectacularly. This is really an ongoing area. And when I say ongoing, on Friday, today is Monday, on Friday I got an email from Miguel Martin strengthening this result. So, I mean, work continues. Now I should mention a result of Daniel and Paquito from their youth, which is that every infinite dimensional Banach space admits an equivalent norm such that the norm attaining is lineable. And what I don't know, but maybe I bet Paco or Daniel know, is whether there's a same kind of result where NA of X is not lineable. And I don't know that, but maybe they do. Okay, so I really want to finish with just a couple of questions. And I mean, let's imagine somehow a real life situation. You're walking home last night from the Casa Balbino, and you meet somebody on the street from Sanlúcar, and he asks you, he gives you a set, and he asks you, is this property from this set is it a lineable property? It happens all the time, I'm sure. But what happens? How do you guess? I don't have any intuition. In each case, property, and I don't have a feeling about how even, what I do know is that there are very many papers which show lineability, that you do have subspaces. There are very few which are, but that doesn't prove anything, but that there are very few where Thank you very much.
Thank you very much for the amazing talk. Are there any questions, remarks, Professor Simio? Any other questions or remarks? Okay, I'll just make. I was just looking at the questions that you posed before, like in 2008. I found an example of, this is just an example, not a renorming, of a non-reflexive Banach space. It's actually a quasi-reflexive Banach space in such a way that the non-normative functionals is not even too lineable. And as and actually I was thinking of probably renorming a space, non-reflexive spaces in such a way that they could have some property related to like quasi-reflexivity, or at least that the space is a maximal subspace of its bidual. So in such a way, then you get non-lineability, not even true lineability of the non-normative function. But the question, renorming non-reflexive Banach spaces for which the set of non-normative functionals is not lineable. That's still, I believe, is still open.
Yeah, and I should say the example I don't know what you perhaps, but it's C0, null sequences, and it's a renorming equivalent norm of C0. And the work that they do.
Oh, the microphones. Oh.
But now I have to say something more significant. The work with C0 originally, fundamental work was done by somebody called Charles Reed. And it's extremely complicated. Well, to me, it's extremely complicated.
It is complicated.
And the examples the work that follows really use Reed's work. So other techniques would be welcome.
Definitely. Any other questions or remark? Okay, so let's thank our speaker again.
No, esa canción solo se llama ¿te vas a sentar? Vale, pues toca, yo voy a tocar con claro. Cámbialo de sitio, sí, sí. ¿Está encendido? Sí, 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 sirve. Sí, sirve. Okay, perfect. Okay, thank you.
Okay, our next speaker is a very good friend of mine, Alexei Karapetias, and I knew him from 2021, where he invited Fernando and us to join a conference in Rostov, and we are very happy that he is here with us and in this conference. Okay, so our friend Alexei is gonna deliver a talk entitled Hausdorff Beresing and Hausdorff Shoe Operators.
Okay, thank you very much, Paco, and it's my great pleasure to be here to participate in such a great conference. And also, I'd love to say that it's a very good, very beautiful tradition to dedicate a conference to your friends. It's very nice. Well, I will base myself on these papers that recently appeared. Maybe they will be short in order not to disappoint people who want to go to coffee break, maybe. Maybe I'll skip some slides. And basically, I will talk about these first two papers, but some ideas from the other papers I will show also. What are the Hausdorff Beresing or Hausdorff zoo operators? Actually, we invented these notions, and well, it's not regular notions. We just trying to understand what are the classes of operators we can study. But as you see, when you study new classes of operators, or when you invent a new classes of operators, you think what are classical operators in your class that are good examples for generalizations. And of course, first example is well-known Beresing transform, which makes a great deal in complex analysis and real analysis. It plays the same role in complex analysis as a Poisson transform, with the only difference that you have integration over the disk. Also the same definition you have in a unit ball. And of course, you know that Beresing transform plays a great role in mathematical physics and actually in second quantization procedure and in many, many other issues of modern analysis. So what the idea appeared actually when I was a Fulbright professor at SUNY at Albany with Keiichi, and Keiichi is exactly Keiichi operators. So the idea was just because I had free time, I didn't teach classes, so I just thought to invent something. We just thought to invent something new, and what we decided to insert a kernel here. You know what happens if you insert just a general kernel, so you'll have integral operator, and you may consider integral operators, and so on, properties, compactness, boundedness, etc., etc. But again, we had a very nice example in our class, so it kind of first motivation for study classes, just we called Berezin, Hausdorff-Berezin. So, but still, okay, this is the case. I didn't mention that this would be Möbius transform. This is the case of the unit disk. It's kind of easy case. And in the case of unit ball, you have these automorphisms, also very well-known automorphisms, and you can define the same way the corresponding Berezin transform and generalize this is the Berezin transform for the unit ball. So you can define the Berezin transform, and then of course you can insert here a kernel and consider more general operators. So that's our idea. And well, this kind, what I said, this is the case of unit disk. We put here a kernel. So actually, if we don't, we consider general measure here. This is just an example. If you have hard measure, then you can put the transformation here in the kernel. So there's kind of symmetric formula. It's very nice. In some cases, it's useful to consider this particular case because you have the symmetry property. You can get more detailed results. Okay. Well, I said that it's good to have, when you consider new classes, it's good to have some examples in your classes operators. And the main example, Berezin transform, but still we have in our class the so-called invariant green potential. It also realized as our Hausdorff-Berezin operator with a specific kernel given by this formula. And still there are more operators and kind of averaging operators in work by Matelievich and his advisor, research advisor, I don't remember the name now, but they considered the operators to prove Farelli-Rudin theorem for p between 0 and 1. So there's also a very useful operator, and this operator is also from our class if you consider such kernel. So having this, let me come back to the first slide. Here's our idea was to take Berezin transform and put here a kernel and consider a general operator, and we did this. And also, when we did this, I came to Kehit Zoo and said, okay, what if we switch the variables? If you put W here and then here, some kind of symmetric switch, and probably nothing happens, but the operator changed drastically. He told me that it's not of interest because he showed me his paper, 1991, where he studied this operator, and this is very small operator. It's one-dimensional operator, so it just takes holomorphic functions and cuts everything, expects the z constant times z to the power 1. So it cuts holomorphic functions. Well, later, my friend Professor Mirotin from Belarus came with a new paper on generalization of this operator. I'm sorry, it was not by intention. And I realized that, yes, this operator is still worth to consider because when you put here a kernel also change operator very much. Well, I will show you that if the kernel will be holomorphic, then this will be still small operator, it will be one-dimensional. But if the kernel will be different, the situation will change drastically. Okay, so from that time, together with Mirotin, with some other co-authors, we consider these operators as a pair of operators because now we understand that these operators, although different from each other, still they are of a great interest for developing the theory. Okay, so in my talk, actually, I will not only generalize the Berezin transform, but the opposite operator. So the idea to put here a kernel, like here you see, to put here a kernel and see what happens, and consider the class of these operators. Well, actually, operator of the second type, let me call it second type, is easier to consider. You can apply some criteria, you can even get some nice necessary sufficient conditions, etc., etc. So let me not take your time on this. As I said, here is a case where your kernel is not only allomorphic but plus multiplier plus radial multiplier. Then it acts on
Entonces se convirtió.
monomials like this. So it's almost radial, it's almost diagonal. So it's, as I said, when you have just a holomorphic function, it's one-dimensional. When you put something different from holomorphic function, in the operating change, in this case, for instance, you can calculate the spectrum, etc., etc. So having this, you can go further with some corollaries, you can prove some compactness, etc., etc. So let me show, for instance, theorem about nuclearity in Berman space. Berman space is the intersection of Lebesgue space with space of holomorphic functions, and very well-known Hardy space. So the operator is nuclear in these both spaces, provided these conditions satisfied. So let me not read this theorem. We have also estimation for the nuclear norm for traces, etc. And well, for the case, this was the case of a general kernel which has a holomorphic part and which has a radial part, non-holomorphic. But let us come back to holomorphic kernels. If you have only holomorphic kernel, a general holomorphic kernel with no restriction, okay, then still this operator is two-dimensional. And you can calculate the action of this operator on holomorphic function as in this formula. Here the additional function is calculated by this series, okay? So you can estimate the norm of this operator. So the situation changed very much from the case of non-holomorphic kernel to the case of just a general holomorphic kernel. It's still two-dimensional, as Kehidzu told me in the case when he had kernel phi equals to 1. Okay? Okay, you can have some further results, calculate spectra, etc., but it's easy because you know it's almost spectral representation, yes, for the operator and Berman spaces. I will keep this slide also. Again, let's come back to the radial case, because radial case is also of interest. If you have a radial kernel, then your operator is diagonal. You can have some corollaries from the theory. You can prove boundedness in the general space of holomorphic functions with the only condition that this space of holomorphic function, in this space you must have denseness of monomials. This is the only condition that we need to prove these statements, all these statements. Okay, and also we can go further to use a recent book by Serbian authors, Miller, Sarsenovic, and so on, criteria for, or sometimes necessary and sufficient conditions for boundedness, because we know the behavior of spectra for this operator, so we can apply the criteria, so sufficient conditions to get boundedness, necessary and sufficient conditions for our operators. But you see, in this theorem, we say our statement is like this. Let spectrum looks like this. Let spectrum behaves like this. Then we have the following boundedness results. But later we decide to put conditions on the initial kernel. It's very natural. Okay, so you don't guess. Just say what are the conditions that we need to have the proper behavior of the spectrum. And to this end, with Professor Grudsky and Mirotin, also we developed a paper based on some kind of asymptotics, so you can actually provide this general asymptotic for the spectral numbers of the operator. And from this we can have many corollaries, and I will not read all of the results. For instance, if you consider average of the initial kernel, then you under these properties you will be sure that your spectrum looks like this. The behavior of your spectrum looks like this, okay? And then you go with boundedness conditions and compactness conditions, okay? Again, you know, we can represent our spectra via Jacobi polynomials, and then we can apply what we know from the classical books on Jacobi polynomials, but the results will be weaker. So what we did from scratch, what we did from the beginning was better because we directly applied the method of stationary phase to the integral representation of spectrum. So this result is kind of weaker. Okay. Um, well, again, we can formulate properties for the now for initial kernel to have proper behavior of the spectrum, and then actually to have boundedness conditions. Here we have a theorem with some statements. You can read. Let me not read this slide. We have boundedness from different between different Bergman spaces here and here also. Well, sorry. Um, Actually, as I said, it worth to consider a general measure. So let me be a general random measure on the ball. We need this property that we call this property tame space. It's written here. We didn't find this property in the literature, so we invented this name, but maybe people know already this property. Well, under this condition, we need to this condition to prove this classes of spaces satisfy to these properties, these classical spaces. But we need this for our technical purposes. And under this property, we can easily prove the boundedness for the general operator with this, I guess, nice condition. Here, the constant depends only on the f. Okay, and here the theorem is for a general space, Möbius invariant space, okay, with the tame property. And actually we can specify conditions for classical spaces, particular cases as examples, block space, Venetian analytic bounded oscillation space, and Bezoff spaces, Bezoff space of holomorphic functions. So every time constant depends on space, and you have these conditions for boundedness. Going further, considering boundedness in LP, in weighted LP, we invented this definition of admissible weight. We call weight and the unit ball admissible if this holds. This inequality, there is a measurable function, psi z that inequality holds, and strong property if you have the symmetrical inequality from below, okay, this one. If you have this one, then we call this as strong property. Classical examples of weights, like this weight and every power of this construction is admissible weight, and we can calculate easily the bound for this weight, the function c that appears in the definition. And having this result, we can formulate the boundedness condition in a general weighted space with a general random measure. So if this constant is less than infinity, is finite, then we have boundedness in a general weighted space, of course with admissible weight. And to have necessary condition, we need the we have this also slightly different condition. You see here is sigma between 0 and 1, so it can be as close to 0 as you imagine, but we cannot take 0, unfortunately. Okay, so that's why I'm saying that this they almost coincide, but they don't coincide, of course. We can specify results for particular weights, of the type 1 minus z squared to the power alpha, which is very important in complex analysis. And of course, you have better conditions for boundedness like this. We don't anymore have a constant. We have just explicit condition for boundedness, sufficient condition for boundedness, and necessary condition for boundedness. And well, also conditions we formulate conditions in some classical spaces. You can see here a very nice condition for Hardy space. Actually, we can apply these operators. Why we consider these operators? Because the initial idea was to transfer what we know for operators with homogeneous kernels to complex analysis. There is a big theory of operators with homogeneous kernels, real analysis, and integral equations with these operators, etc. So we thought that these operators are kind of replacement in complex analysis of this kind of homogeneous operators. It's not actually, but the technique of operators with homogeneous kernels applied to this case very successfully. So we can use this technique and prove some boundedness results, but I will not have slides on this idea. I proceed with last slide of Hausdorff operators. Here you have approximation. Actually, it's easy to construct approximation within the LP spaces. Here is just example for nice measure, just not to formulate a big theorem. So this construction that we consider give you a very nice approximation, having in mind that it does not damage holomorphic function. That is a good idea to have in mind that we can approximate a holomorphic function by these nice constructions. Okay, that's the idea. And well, let me repeat some ideas for Hausdorff-Berezin operators, kind of counterpart of Hausdorff operators. I will not repeat all the theorems, just some examples. Here, for instance, here I have slides for technique for operators with homogeneous kernels, I'm sorry. So, for instance, if these constants are finite, then you have boundedness in these Lebesgue spaces with higher measure, provided these constants are finite. This constant written here. Okay, so this theorem obtained by the exactly using technique of operators with homogeneous kernels, reduce it to the case of complex analysis. We can formulate some compactness results, but let me skip because I need to say a lot of waste a lot of time for definitions. But you can see the nice conditions for compactness. Okay, so the following theorem holds true for this Hausdorff-Berezin operator. And let me just, I guess I already go further than and finish my talk with this nice example. This has nothing to do with my talk actually, because it's just one-dimensional case. But after we started the study of Hausdorff-Berezin, Hausdorff operators, doing which like things like this, we found a paper on operators of this type. This operator just one-dimensional on the -1 interval, real operator, of course, real functions. So this operator appears in many problems of integral equations and Bizadze, Lavrentiev equations, actually Prandtl equations, and so on. So we found it very interesting because formally it's a restriction of our operator to the real line. We cannot say this because it's not true. It has no mathematical background, but formally it looks like this. You just restrict from the unit disk on the interval -1, 1, and actually what we figured out that we can apply the same technique to these operators. Now we are in process of the study of these operators, because these real operators, real line operators, also important. And here, for instance, Fourier transform. If you have higher measure, not general random measures, then we can do Fourier transform, Fourier calculus, because it just can be reduced by the real line. Of course, you cannot do this when you have here random measure, so what we do with my student now, but this just to show you that these operators appear, for instance, in these general integral equations. And these general integral equations contains these well-known Prandtl, Tricomi, Lavrentiev, Bizadze integral equations. And we hope we can generalize this technique for generalization of these classical integral equations. Well, thank you very much.
Thank you very much for the extremely interesting and very nice talk. Are there any questions? Or Professor Semyon, please. Oh, yeah.
Yes.
I'm talking about invertibility properties. Because you show this approximation result is quite regularization, quite interesting.
This is the next issue that we want to study, because actually we just started to work with this one-dimensional operator maybe just 6 months ago, maybe. But it's a very good question, because when you study integral equations, of course, you want to have
For us, it's
a closed invertibility property, of course.
It's quite important for transform theory.
Yes, but also the approximation gives you the idea how to construct the inverse operator.
I don't remember if Mirotin studied these problems.
Excuse me?
Mirotin, our colleague, Professor Mirotin, studied these invertibility properties. I'm not sure.
No, within the place, no.
Because this Bayesian generalization could be interesting to invert.
Yes, it's a good idea. That just matter of time,
Okay.
Thank you.
Thank you. My question is this. I would like to know if there is some studies about the dynamic of this kind of operator, Hansdorff operator and Hansdorff Brazilian operator. Precisely, if we can iterate this operator and obtain some subsets of operator to compare with the whole space.
To be honest, I don't hear you well and don't understand what your question.
I ask about the product. If we iterate the whole
product. Okay,
yes.
Okay, good. Yes, actually, I skipped the slide, but if you take Haar measure, then you can multiply operators. You may give conditions under which your product of two operator will be again Hausdorff-Brezen operator. So you can consider algebraic properties, stuff like this. Yes, you can do this. Yes.
And up to now, we don't know the kernel.
I just have one paper in algebra, so I'm not good in algebras. But since your question is very good, because let me find this slide. I skipped this slide, and this is a very good question, also open question. Let me see. Just 1 second. No, maybe it was at the end. Here. You see? For instance, this condition, well, this you can consider operators with two variable kernel. Because when I use just one variable. But of course you can insert two variables, but under this condition, this is only if and only if condition for the two variable kernel to be the same operator. But more stronger condition gives you radial case in the unit disk. This condition gives you radial case. So you not only have Hausdorff-Brezen operator, but you have Hausdorff-Brezen operator with radial kernel. And in this case, for sure, you can multiply operators. You'll have the same type of operator with another radial kernel, so you can consider algebraic properties, everything like this. So you can do this. But your question is very good, because I don't know answer in the case of the unit ball. Here, the problem is open. Whether the same condition will give you the radiality of the kernel. Why I don't know, because in the case of the disk, you just can take Möbius transform, you can
calculate one variable from another, etc. But in the case of unit ball, you have such a great, such a lot of calculations. So I have no idea how to calculate, how to, you see, what I mean is W equals to Z. How to find W? It's easy. You apply the same transform. You have W equals to Pz of Z. But how to find Z, I don't know in the case of renewable. If I know that I can do the same thing. But this equation is open equation. What we can do in. But again, since I'm not doing algebra, so maybe I just kept this.
Excuse me, just about convolution product, I think it's also probably possible to construct some convolutions, a convolution product formula for your kernels.
Yes.
I don't, maybe it's very nice for then construct convolution theory.
Yeah, of course. In the case, the one-dimensional operator in the case of Haar measure is nothing but the regular convolution of the real line. You just go to the real line.
Exactly. Yeah.
Yes. In the case of general measure, not, but you still can calculate. You still can invent some theory of this same type.
Thanks.
Thank you.
Thank you. Any other question or remark? Okay, then Okay, so then let us thank the speaker again. And we have a break now for coffee, drink, or whatever you feel like. going to be delivered by Professor Lajos Molnar from the University of Szeged. Lajos is also a very good friend of us. We met him in 2017 in a conference that he organized in the Bolyai Institute of Mathematics, which is probably the most famous mathematical institute in Europe. It was founded by Hard and Rist. Okay, correct. And so it was a conference, 2017. We met there, very good friends. Actually, in that conference, I met Kenyer Castillo and some other friends. And so we had a great time in Szeged with Lajos. And yeah, we spent very good time in that conference. So we are so happy. I'm grateful to him that he could join us on this wonderful event. And so I'm really deeply thankful to him. So he's going to speak on order isomorphisms between positive definite cones in sister algebras and their applications. So, go ahead.
Thank you so much. I don't know, can you hear me? Yeah, but yeah, you can. Yeah, but you said that then the camera cannot see me.
Well, no,
but,
from here I can see you.
Okay, maybe this way. So I'm very thankful to the organizers, especially to Paco, for the kind invitation. It's really a big pleasure to be here. I enjoy Spain, every part of Spain, I have to tell, but I visited Granada, for example, so this part of Almeria several times, so Andalusia in general, so I feel like at home. So thank you so much. And so I would like to speak about certain isomorphisms between certain parts of C-star algebras. Those parts are the positive cones, and those isomorphisms are so-called order isomorphisms. And actually, this is a survey of some recent applications of a former result, which tells that the positive homogeneous order isomorphisms between positive definite cones of C-star algebras are automatically additive. So you don't assume additivity, you assume that your transformation is a bijective map preserving the order and it is positive homogeneous. In that case, this is automatically additive. This is the result what we use here. And as an application, we will determine the structure of certain mean preservers, certain isometries. Let's see how much time I will have. So our basic structures are C-star algebras, and we always assume that those are unital. And we have the self-adjoint part, the positive semi-definite part, and the positive definite part of the algebra. A positive semi-definite element means positivity, that's the terminology what they use in operator theory. So that means the self-adjoint and the spectrum is non-negative. Positive definite means that this is a positive semi-definite plus invertible. And okay, so A plus is usually called the positive semi-definite cone, A plus plus is called the positive definite cone of the C-star algebra, and we have the order, which is of fundamental importance here. This is the usual order coming from positive semi-definiteness. Sometimes they call it the Loevner order. So A is less than or equal to B, if and only if B minus A is a positive element. Okay? And we also have a very important concept, which is the notion of Jordan-star isomorphism, also called C-star isomorphism. So a bijective linear map. It's important to emphasize linearity here because in our results, we don't assume linearity. So linear map between C-star algebras is called Jordan-star isomorphism or C-star isomorphism if it preserves the Jordan product, AB plus BA, and also respects the adjoint operation, okay? Those maps are commonly called as the most important symmetries of C-star algebras. And the transformations, what we are considering and concerning which we have the result which we will apply, are order isomorphisms. What is an order isomorphism between the positive definite cones? It's just a bijective map preserving the order in both directions. Easy. Positive homogeneity, the meaning is obvious. And there are examples for such maps. For example, if you take a Jordan isomorphism between the full algebras, then the restriction to the positive definite cones will obviously be positive homogeneous order isomorphism. The other type of examples are the congruence transformations. So if you have T, a positive definite element, then this transformation which sends TAT to A, again, when you restrict it to the positive definite cone, it's an order isomorphism, which is positive homogeneous, clear, trivial, easy. And the somewhat surprising fact is that the converse is also true in the sense that there are no more examples for positive homogeneous order isomorphisms in the following sense, that if we have two C-star algebras A and B, and we have a positive homogeneous order isomorphism between the positive definite cones, then it is necessarily a Jordan isomorphism and the composition of a Jordan isomorphism with a congruence transformation. So there are no more good examples. And actually, this result is just a trivial consequence of another result of ours, joined with a Japanese friend of mine. It's about so-called Thomson isometries. I will give the details in a moment. So the main point here is the additivity of positive homogeneous order isomorphisms. So when you have a transformation preserving only the order and respects positive scalar multiplication, then addition is also respected. Oh, so you get it for free. That's a quite surprising thing, at least it was for me. So the topic, the content of my talk was written in this survey paper, which appeared recently in Fields Institute Communications. Okay, so I mentioned Thomson isometries. What is a Thomson metric? This is a famous metric on the positive definite cone of C-star algebras. The original definition is valid, or it's functioning, or not only in C-star algebra, but in more general circumstances as well, but here we restrict our attention to C-star algebra. So this is the general definition. You see that for defining this quantity, you need the order and you need the scalar multiplication. Okay? So you see that if you have a positive homogeneous order isomorphism, then this will be Thomson isometry, because the Thomson isometry is defined in such a way. We can give an explicit formula for that distance, and this is this one. So the norm of the logarithm of this complicated product, what you can see there. Why this, and this is a metric. It's not trivial to see that it is really a metric. From this definition, you can see that it is a metric. From this one, it's very difficult to verify. What is the importance? The main importance of this metric is that, believe or not, this is the topology is the same as the norm topology. But with this metric, the positive definite cone is complete. You know, in the norm, it's an open set. It's not complete. With this metric, this is complete. So, for example, you can apply Banach fixed point theorem and so on, and that's the reason why they use this metric on positive definite cones. Okay, so we were interested in describing the corresponding isometries. What are the isometries? Okay, few examples. Once again, one can easily see the Jordan star isomorphisms when you restrict them to the positive definite cones. They are Thomson isometries. For the same reason, I mean, again, simple, quite simple to see that congruence transformations are Thomson isometries. And there is a third example, namely the inverse operation. So if you take the inverse and you take the logarithm, you will see that this will be just the negative, but because of the norm, it will be the same. So you can easily see that the inverse operation is again a Thomson isometry. And it turns out now we have 3 prototypes of Thomson isometries, and we can see that from those 3 prototypes we can produce all. This was the joint result with Hattori that appeared in Journal of Mathematical Analysis and its Applications. So you see that the statement is that if you have a surjective map between positive definite cones, it is no linearity is assumed. So just an isometry preserving the distance. Then, so this is a Thomson isometry if and only if we have a central projection P in B and the Jordan star isomorphism between the full algebras A and B such that it can be written of that form. What is it? You see the two-sided multiplication, the congruence transformation, and inside you see a Jordan star isomorphism and the Jordan star isomorphism composed by the inverse operation. So from those 3 types of transformations, you can really obtain all Thomson isometries, and this is an if and only if statement. How can we get our result, our proposition, which I mentioned before? This was about positive homogeneous order isomorphisms. We have seen that positive homogeneous order isomorphisms are Thomson isometries. Therefore, they are of that form. But I assumed positive homogeneity. In this part, it's not positive homogeneous because that is the inverse. So that means that this part is not there. What remains is just a Jordan star isomorphism and a congruence transformation. Okay, and when studying, let me point out an interesting fact that when we study Thomson isometries, this was not the way we proved that result. This is an observation what I made after that. Okay, let me first recall the famous Moser-Ulam theorem, which says that if you have 2 norm spaces and you have an isometry between them, linearity is not assumed, just a distance-preserving map, a surjective one, then it is automatically affine. And here the proof, the main part of the proof is to show that between norm spaces, every isometry preserves the arithmetic mean. And in that paper by Moser and Ulam, this is done in the way that they characterize the arithmetic mean entirely using the metric of the norm. Entirely, nothing else. And if you follow their characterization, Moser-Ulam characterization, but you change their argument at many places because their structure, a norm on a norm space, concerns the additive structure, which is commutative. And here, this metric, you see that the multiplicative structure is involved, which is non-commutative. So you have to be very careful. But the point is that if you follow the machinery of Moser-Ulam, you change appropriately their argument, you will obtain that you will have a complete characterization of the so-called geometric mean, okay, using the Thomson metric. And that implies that, and this is the geometric mean of two positive definite elements, which is much more complicated than the arithmetic mean, you see. And so you can see that Thomson isometries are automatically preserving this mean, this geometric mean. And okay, as I said, the proof was different, but now the problem naturally arises that what are the maps between positive definite cones which preserve the geometric mean, okay? Because every Thomson isometry preserves the geometric mean. Okay, this is an independent question. Actually, this is an algebraic question, because now we have the positive definite cone equipped with this operation, which is not a very simple operation. And we are asking, what are the corresponding isomorphisms? And actually, we don't have a result for general C-star algebras. We have a result only for von Neumann factors. So for Neumann algebras with trivial centers. And on finite von Neumann factors, there is a unique normalized trace, which we will denote by trace. And here is the result, that if we have two von Neumann factors, and we have the positive definite cones, and we have a continuous map between them, without continuity, the conclusion is not true, so this is an essential condition. And we have a bijective continuous map, then we have two cases. We have the infinite type case, and we have the finite type case. In the infinite type case, you see that those maps are exactly the maps which originate from algebra star isomorphisms or algebra star anti-isomorphisms. Also, the inverse operation can appear here, and we have this two-sided multiplication, the congruence transformations. It's easy to see that any such maps are preserving the geometric mean. The converse is not easy to show. And the situation is even more complicated in the finite type case. Finite type case, you can think of matrices. And on matrices, there is this functional, which is called the determinant. The determinant is multiplicative, and from that it follows that it preserves the geometric mean. And this shows up, that kind of functional shows up also in the more general case of von Neumann algebras, I mean finite factors. So beside this part, this other part also shows up, which can be considered as a certain power of the determinant. And this is the complete structure. And then, as for C-star algebras, we don't know. We don't know the structure of geometric mean preservers. We have only a certain class of means concerning which we have the structure of mean preservers, and the proof depends on this result concerning order preserving positive homogeneous order isomorphisms. So just two sentences about general means, general Kubo-Ando means. Let me show the shortest way to them. So we have a scalar function on the positive half line, which is operator monotone and normalized by this condition, and then we form this operation, and this is called Kubo-Ando mean, the Kubo-Ando mean corresponding to the function, the operator monotone function f. And there are, okay, let me a little bit change the order. So if we take this function, 1 plus t over 2, or the square root function, or 2t over 1 over t, Then we obtain the three most fundamental means: the arithmetic mean, geometric mean, harmonic mean. This is not a surprise. That is not a surprise. This one is a little bit of surprise. And then, what are the mean preservers? So once again, there are candidates. One can again see that every Jordan star isomorphism, they preserve everything. So they are the best transformations. They preserve everything, so they preserve also the Kuban domains, and once again, the congruences are mean preservers. This is not very easy to see, but this can be shown. And one can think that that's all. No, no, no. This is not all, because if I go back to this result, you know, this functional part appeared. So in general, there might be other preservers, but concerning a certain class of means, and those are the so-called power means, which correspond to the, let me see here, correspond to this operator monotone function. So those are the corresponding power means. One would like to define the power mean in the most simple way: A to P plus B to P over 2 and P's root. You can do this, but this is not a good mean. You may like it, but it is not a good mean. This is a good mean. This is the good power mean. And in that way, you get a path connecting the arithmetic mean and the harmonic mean, and when P goes to 0 here, then this quantity goes to the geometric mean. So you have a one-parameter family of means connecting those three fundamental means, and then what is interesting, that we can describe the corresponding mean preservers without any additional assumptions. So if we have C-star algebras, P is not 0, because the 0 case is the geometric mean case, and this is a different case, we have seen. But if it is not the geometric mean, but a power mean, in that case, a bijective map preserves that mean if and only if it is of this simple form. So once again, here I don't assume anything, only that it is an isomorphism in the algebraic sense, an isomorphism of the positive definite cone with respect to this operation. And P is just one P, not for all P, just one P. Then this transformation is a composition of a Jordan star isomorphism and a two-sided multiplication. Okay, I skipped the proof, and okay, let me just show you one more operation. This is not a Kubo-Ando mean. This is also a mean, a Wasserstein mean, recently defined by Bhatia, Jain, and Lim. This is the operation. It's not very simple, right? And I can describe the corresponding isomorphisms. Once again, the same form. There is one difference, that here this C is central. It's a central element. It commutes with everything. And once again, this is a if and only if statement. So it's a precise description. And let me conclude with so this is what I know about mean preservers, applications of the first result that I mentioned, and we can describe using that result about positive homogeneous order isomorphisms. So we can describe the so-called Bure-Wasserstein isometries. And let me mention this result in some details. So maybe this Bure-Wasserstein metric appears also here for matrices, okay? This is that quantity. It is a true metric. It's not easy to see that this is a true metric. if you consider matrices, there is a nice trick how to prove that this is a true metric. But we are interested in the C-star algebraic version of this result. And anyway, for that we need the concept of a trace. This is a positive linear functional, which is tracial. That means that it vanishes on commutators. And we call it faithful if the trace of a positive element, whenever it is zero, it implies that the element is zero. As I mentioned, on finite von Neumann algebras, there are traces, and there are also some kinds of C-star algebras where there are traces, but not on all C-star algebras we have trace, that's clear, but there are classes of C-star algebras, and then we can define formally, it's very easy to define the Bures-Wasserstein metric. We consider this quantity, which is anyway called the fidelity. This metric plays important role in quantum information science, so that's the reason why they call this part fidelity, and this is the definition of the metric. But you know, for matrices, using a trick, one can show that this is a true metric. In the C-star algebra case, it's much more difficult to show that it is a true metric. It was done by Faranik and Rahman for C-star algebras. So this is a true metric, okay? This is a fact, and the question, what are the corresponding isometries? And the result, once again, an if and only if statement. We have that whenever we have two C-star algebras with faithful traces, we have a surjective map between the positive definite cones. Then this is a Bures-Wasserstein isometry if and only if, once again, we have a Jordan star isomorphism, and once again we have a central element such that the transformation can be written in this form. And there is one more condition. So this is a precise description, an if and only if statement. How to prove it? Before that, I didn't mention proofs. Here, just the idea of the proof. The previous proofs were also like that. So the key thing is to use our result on positive homogeneous order isomorphisms. What do we have to do to use that result? We have to show that our transformation is an order isomorphism which is positive homogeneous. How to do this? Here we have a very simple characterization of the order. So using the Bures-Wasserstein metric. So we have that for two elements A and B, positive definite, A is less than or equal to B, if and only if this set of numbers. So those are the differences between squares of distances. Those are numbers. So this set of numbers is bounded from above. This is a characterization. It's not very easy to see, but not difficult to see, that A is below B if and only if this set is bounded from below, from above. But because our map is an isometry, isometry preserves the distances. So our isometry will preserve, will transform this set to the corresponding set with phi of B and phi of A in the place of B and A. And then boundedness from above is preserved because the set is preserved. So we obtain that Bures-Wasserstein isometry is an order isomorphism, and then with some tricks one can show that it preserves the trace, and then if it preserves the trace, then it also preserves this fidelity, and this fidelity encodes positive homogeneity. Okay, it's not exactly positive homogeneity, but it's kind of multiplicative thing. So you can show positive homogeneity, and then you can apply our first result that I mentioned, the basic result. So it is of this form, a two-sided multiplication composed by a Jordan star isomorphism. But there is one more thing, because I said that this two-sided multiplication corresponds to a central element. Why it is central? For me, it was a surprising thing that if we have a Jordan star isomorphism, and we know that this operation, this transformation preserves the trace, and actually this is phi, you see, and I mentioned that phi preserves the trace. So if it preserves the trace, then it forces T to be central. This is again a nice argument to show. At least I like that. So to finish, let me remark that quite the same method was applied to describe various relative entropy preservers, Rényi relative entropy, Umegaki, Belafkin, Stashevsky relative entropy in the C-star algebraic setting. And we also have results as a combination of norms and means. I mean preservers of norms of means, but so of course I don't have time to speak about them. And let me show the references. Those are the references of that survey paper. That survey paper contains much more results. I mentioned only 2 or 3. Okay. This is Thomson's original result, where he introduced that metric that I mentioned. And thank you so much for your kind attention. Ooh, I was a little bit late.
Okay, thank you very much for the very interesting talk. Are there any questions? Okay, I'll move forward. Yeah. Move away from the speakers. Are there any questions or comments? Okay, Professor Singh.
Okay, so what is the central projection?
This is a projection which is central. Central means that it commutes with everything.
Okay, commute with everything.
So for that reason, okay, let me go back. It's a kind of direct, so what you have seen there, it was a kind of direct sum. Yeah, there. So it's a direct sum of this Jordan isomorphism and the Jordan isomorphism composed by the inverse transformation. P is a central projection, so it's a projection.
So that means you put on both, either side is okay.
Yeah. Commutes with everything.
And also you mentioned the continuity, I think, in one of your theorems cannot be dropped. So
this is about the geometric mean. Maybe not here, but later. Yeah. It's essential. That is counterexample.
So does it mean that can it be replaced by another property?
Actually, what is my guess? Okay. As for matrix algebras, okay, as particular operator algebras. So for matrix algebras, maybe you can replace this by measurability or some weaker regularity. Actually, I think that there is a possibility to describe all such transformations, but the description would be more complicated.
So you need some condition, at least, right?
Yeah, and let me continue. If you consider the full operator algebra over a Hilbert space, and if it is infinite dimensional, actually I conjecture that no need to assume continuity. But full operator algebra, Hilbert space, infinite dimension. I don't know the proof, but this is my conjecture.
Okay, thank you.
Thank you very much. Any other question or comment? I have a small question. Like last time that you were in Cadiz, I remember we were talking about in general, central elements of a sister algebra. So they could be like, depending on the sister algebra, they could be completely different. Like, not.
So in those investigations, no, in my recent investigations, the centrality shows up in several places, and that talk was about centrality. So that was a different thing. Anyway, I recently published a paper, Journal of Mathematical Analysis and Applications, where I collected those results.
I'll look it up.
New kinds of characterizations of centrality, central elements. So you know, I'm doing my work, and centrality shows up in different different fields. I mean, that's interesting.
Okay, that was my question. Thank you. Any other question? Okay, so let's thank the speaker again.
Thank you.
Okay, our next speaker is also a very good friend of us, Vladimir Kravchenko. We also met him in Rostov in 2021, in several times in Armenia, and we are extremely happy to have him here together with Alexei and the rest of the colleagues from the OFA network. So in particular, I am deeply thankful for you for having come here and join us in this conference. Okay, so our friend Vladislav, he's going to speak about serious representations for solutions and reconstruction techniques in inverse coefficient problems.
Thank you very much, Paco. Many thanks to the organizers for this opportunity to present my recent work to this great audience. This work will consist of mainly of two parts. So first of all, we will discuss this simple question: how to solve linear second-order differential equations with variable coefficients. And I will show you the way to construct so-called Neumann series of Bessel functions, which give a very attractive form of writing a solution of general linear second order equation. Next, we will consider a very general inverse coefficient problem. I will explain why is it so general. Then we will see how we can solve this general inverse coefficient problem using the Neumann series of Bessel functions, with some numerical illustration to convince you that it really works. And some words in the end about inverse problems on quantum graphs, just some words. So this is the plan. And I will talk mainly about the Schrödinger equation here. So Q of x will be quite general from L1 space. L here, this L is finite, so we will consider in this talk only problems on a finite interval. Q, and it is important, Q here in general is complex valued. So of course, many results here are applicable in a much more general case because there exists such a nice Liouville transformation which allows us to transform a more general second order equation into the Schrödinger form. So first of all, I will need just a couple of notations. We will denote two solutions of this Schrödinger equation as C of rho x and S of rho x. They will satisfy these initial conditions at the origin. So we write here this rho to make it clear that they are, for example, when I fix x, I can consider them as functions of the spectral parameter rho. It's very convenient. So C satisfies the same initial conditions as the cosine, and S satisfies these conditions, so it's 0 at 0, and its derivative is 1. Now, just to remind you that any series of this type, so some coefficients by the Bessel functions where this nu is fixed, and we are changing this n from, let's say, from 0 to infinity. Such series, they are called Neumann series of Bessel functions. This is just a quotation from the Watson's treatise of 1922. And the first who considered this kind of series was Carl Gottfried Neumann, not von Neumann. It was in 1960 something. And later on, Gegenbauer made a lot to develop the theory of such series. So there are many papers and books dedicated to this kind of series. So they are quite known object in mathematical analysis. But in fact, I will show to you that they arise very naturally in the theory of differential equations, which is quite surprising. And especially, they are very convenient for inverse coefficient problems. So with the help of the Neumann series of Bessel functions, I will show to you that we obtain not just a representation for solutions C of rho x and S of rho x, but a representation which is uniformly convergent in any strip in the complex plane of the variable rho, of the spectral parameter rho, in any strip parallel to the real line. Okay? Why this property is that important? Because when you solve direct or inverse spectral, for example, problems, you need to work with small spectral parameter and very large spectral parameter. It's very convenient. So these representations give you, you just consider the truncated sum of such representations, and you obtain the fantastic property that this truncated sum approximates well not only your solution for small rho, okay, but also for very large rho. Okay, you obtain a very nice approximation. So you will see it in a couple of minutes. So first of all, how we arrive at such kind of representations. Everything begins with these so-called transmutation or transformation operators. This is an object which is very well known since the work of Soviet mathematician Povzner of 1948. He proved that for our solutions, C of rho x and S of rho x, there exist these two representations. So there exist continuous functions, C of xt and S of xt, the kernels of our integral operators, which work in the following way. So these representations are for any rho, for any complex rho. So here the important feature is that the kernel doesn't depend on rho, okay? So you just, if you, suppose you know the kernel somehow, C of xt, okay? Then this is just a second kind Volterra integral operator, which is the best operator, best possible integral operator, okay? You can imagine, with a continuous kernel, what else you can wish, yeah? And the kernel doesn't depend on rho. So you solve everything for your Sturm-Liouville equation, for example, okay, using this kind of operators. The problem is that nobody knows how to construct these kernels, okay? But they exist. They exist. And there are a lot of books where there is a lot of information about these kernels. For example, the well-known book by Levitan, Inverse Sturm-Liouville Problems, Marchenko, and so on. There are hundreds of books about this. So what we succeeded was to just to construct this kernel, in fact. So in this paper, joined with Luis Navarro and Sergei Torba of 2017, we proved that these kernels, for example, the kernel C of xt, they admit such a nice representation with the Legendre polynomials from the first talk of this conference, okay? This is just Legendre polynomials, and the most important point here is that these coefficients Gn of x, they can be constructed. For example, if you solve a direct problem, so you know the potential Q, you just can construct this coefficient by a simple recurrent integration procedure, which looks like this. So you have some Cn of s, which are known, okay? And you integrate the previous one multiplied by this, and you obtain the next coefficient, okay? But for us, we don't need the formula for Cn of s here, even. We have them, okay? But we don't need it because we are interested in the inverse problem. And for the inverse problem, everything is simpler, in fact, here, okay? Why? Because we know that the very first coefficient in this representation, G naught of x, is just our solution, C, corresponding to the value of rho equal to 0, okay, minus 1. What does it mean? That in fact, if somehow it happens that we find out which is the very first coefficient G naught, we recover Q directly, okay, from here. So somehow we should construct just the very first coefficient, nothing else. And something similar, of course, is valid for the kernel corresponding to the solution S. Okay, we have another representation. Now, what happens if we just take these representations, series representations for the kernels, and put them into our transformation operators? So we just take this representation for the kernel C, put it here, okay? And what we should integrate? We should integrate the Legendre polynomials multiplied by the cosine function here. What we obtain? We obtain the spherical Bessel functions, very good functions, very well described. Everything is known about these spherical Bessel functions. They are introduced in this way. And something similar happens with the second solution. So we have our Neumann series of Bessel functions for the solution C of rho x and S of rho x. They have such a form, okay? And now, why they are so unique and so interesting? First of all, we have good convergence properties. So they, for example, for every fixed x, the series converge uniformly on any compact set of the complex plane of the variable rho. But most important is that the following two features. The first one, which I mentioned, that the very first coefficient is sufficient to recover Q. Why? Because you just recall that this C is a solution, okay? So Q is recovered just from this formula. It's sufficient to know G naught or S naught. It is the same. You recover the potential immediately. So just the very first coefficient. And second, even probably more important feature is that, well, we consider this partial sum, for example, for the solution S. We just truncate the series here. And we obtain these kind of estimates where the right-hand side doesn't depend on the real part of rho. Okay, so this means the uniform convergence in any strip of this kind, okay, in the complex plane of the variable rho. So small rho, very large rho, doesn't matter. This approximate solution approximates equally well our exact solutions. And it is something that you can see on a computer. So there are, of course, much more properties of this kind of series representations, which can be found in this recent book of mine and in our recent book with Alexei Karapetyan's. Here we still receive a lot of critics and comments from interested readers. So one of them here. And well, but more recently, we succeeded even to obtain another representation, but for a slightly nicer potentials. So this series representation is also a Neumann series of Bessel function representation, but it's not only gives us the uniform convergence in a strip, it works even better. It converges better for larger rho, okay, first. And second, to recover Q, you don't need even to differentiate, even once, okay? Q is recovered from just an algebraic combination of first coefficients of this representation. Look, for example, C of rho x has such a nice representation where, of course, cosine is always known, okay? And the first coefficient here, omega of x, is this integral of q, is the primitive of q, okay? Q minus and q plus here, they are introduced in this way. So if somehow we find the first and the second coefficients of our representations, we recover q from an algebraic combination of them without any differentiation. So it's even more attractive. And the convergence properties look like this. So the partial sums, they approximate even better our exact solution when rho grows, okay, when it becomes larger and larger. Okay. And now about the inverse coefficient problem. This is just to make you feel how really how general is this inverse coefficient problem. This is this image just for this. So it's almost so general that look, it's almost like think of a potential and we recover it. Okay, this is this picture wants to say. Think of a potential and we recover it. Okay, just I will now explain why is it. So I call it problem A here in this talk, and it looks like this. Imagine that, okay, we consider our Schrödinger equation. The potential is complex valued. It is from this Sobolev space. And y, okay, we just have some solution for which we know its values at the origin for several rho k, okay? We know the derivatives at the origin of our solution for several rho k, and we know the values of this solution at the end point, at L, for the same values of rho k, okay? So from this data, from rho k, ak, bk, and lk, from this data, we should recover q. Okay, this is the inverse coefficient problem, which of course has a lot of applications and so on. So just here, let us know that in terms of our solution C and S, this solution Y has such a form. Okay, this simple form, just to remember it. So why this problem is that general? First of all, the well-known problem and very important in implications, in fact, the recovery from a while function, it is a special case of this general inverse problem. So in this case, the while solution has such a form, so its derivative at 0 is 1, the solution at L is 0, and the while function is precisely the value of this while solution at 0. Okay, this is just a definition. So the problem consists in recovering the potential Q from the knowledge of this while function. So in our notations, we have that AK, they are just these values of M at the points rho k. BK is 1 because of this. Okay, this is our BK here. And LK are 0 because the values of our function are 0 at the end point. So this is a special case of our general problem. So the famous and classical inverse two-spectrum problem is also a special case. So just trust me from one of the previous talks. Okay, it's easy to see. And for example, the scattering problem on a finitely supported for a finitely supported potential is also a special case. What happens in this situation? So you have the potential Q, which is 0 up to 0. Then it is some complex valued function in general, q of x, and then 0, okay, outside. So a plane wave, for example, this one, is incoming from minus infinity, interacts with the potential, and then the part of it is reflected, the part of it is transmitted. This is a classical problem, in fact. And the part which is reflected, so here the wave has such a form where r of rho is the reflection coefficient. The part transmitted is this transmission coefficient multiplied by the same plane wave. And so the resulting wave outside of the interval has such a form. So for negative x, it is this combination. For x greater than L, we have this solution. And so we can easily rewrite our problem in terms of AK, BK, and LK. So here AK will have such a form because they are values of our solution at 0. The derivative has such a form, and LK, they are these guys. Okay, just rewriting in our terms. So this is a special case of our general inverse coefficient problem. There are much more examples, just let me skip them here. So of course there are some methods which were developed for inverse Sturm-Liouville problems. So for example, these are just some references, but I would like to mention that all these methods are iterative. Our method is direct. None of these methods can solve problem A. None deals with complex potentials because it's just a very challenging problem, and the method which I'm presenting to you works equally well for real valued and complex valued potentials. And many of the methods introduced before, they need some additional information on the potential in order to begin. Okay, for example, the method from here, they need, for example, what is called the mean of the potential, this this integral of Q, which is you can't obtain from anywhere in applications, in fact. So our method consists of 2 steps, just very simple. And in both steps, we use the Neumann series of Bessel functions. So the first step, we immediately from the input data, we obtain the values of our solution, C of rho and S of rho, but at the end point. Okay, just both solutions at the end point of the interval. And then somehow we should convert this information into the information on the whole interval. And this is a very interesting problem. In fact, it arises in a lot of approaches, so it is behind of. And here we propose a new solution for this problem, which is based on a very simple, just trivial observation, in fact. So let us consider a third solution for the same Schrödinger equation, which satisfies these initial conditions, but at the end point L. So we call this solution T of rho x. It is 0 at L, and its derivative is 1 at L. So it's like the solution S of rho x, but centered at L. Okay, let's say. So it's very easy to see that this solution T of rho x has such a nice representation in terms of S of rho x and C of rho x. So these are just these C and S evaluated at L multiplied by the corresponding function. It's very easy to see that this is so, and this is a generalization of this trigonometric identity, in fact, okay, which is the same equality 4, but when Q is 0, okay? So we use this identity for our second step. So the method consists in the following. We take our input data, and use NSBF to obtain C of RL and S of RL. And then having them computed, we put them in this equality, and instead of T of X, S of X, and C of X, we use their Neumann series of Bessel functions representations here, from where we obtain directly Q of X. So how it works? Now, the first step, we substitute this Neumann series of Bessel functions representations in this formula. When LK are known, they are the values of our solution at the endpoint, and we know that the solution has such a form. So here we substitute the NSB of the Neumann series of Bessel functions representations, and we arrive at some system of linear algebraic equations. So for the coefficients omega of L, Q minus of L, Q plus of L, and so on. And these guys are known, okay, from the input data. So from here we compute all these coefficients, including several of the coefficients from these series representations. So this is the first step. This gives us the possibility to obtain these partial sums of our solutions evaluated at L, and for which we have these nice convergence properties, okay, the uniform convergence in a strip, okay. And second step, we just do in fact the same thing. So these guys are known, and we put here the Neumann series of Bessel functions representations and derive immediately at another system of linear algebraic equations, where these are known, AK1, AK2, and so on. These coefficients are known, and what we are looking for is these unknown coefficients, omega of x, cube of x, which is introduced in this way, and so on, okay? And in fact, we just need to recover the very first two of them, omega of x and this q capital of x. That's it. So, because finally the potential is recovered from an arithmetic combination of these two. So it's really very simple and more or less how it works. So what I'm showing to you, in fact, no other method can do something more or less similar, okay? I'm trying to explain why. First of all, a very general problem. So you just take any values are okay, you take your input data there, for example, AK, BK, you can define somehow. For example, sine of rho k, cosine of rho k. You know what are the values of your solution at the endpoint, and you recover Q. Look, here, for example, Q is complex valued, okay? So this is the real part, this is the imaginary part. The real part, if somebody did a numerical computation, probably they know that just when your function changes, so grows, for example, rapidly, or have a very large range of the values, it's already difficult. So the real part, for example, here grows up to 1,000, okay, in the interval from 0 to 1. And the imaginary part is oscillating. The maximum absolute error, which gives our method here, is of order 10 to minus 3, okay? Now, another example for a function, for example, which has discontinuous second derivative, because I'm working with the Sobolev space H1. So discontinuous second derivatives. So, for example, looks like this, and the maximum absolute error is of the same order, 10 to minus 3. Okay, this is more or less how it works in practice. And recently we implemented this method on quantum graphs, which are just you have your Schrödinger equation here on every interval and some compatibility conditions at the common vertices. Okay, so these are very important things, of course, and they are called quantum graphs since the discovery of graphene. Okay, before they were called networks of differential equations. Okay, but so of course they arise in many applications, and they are computationally they are really very challenging. Okay, to solve inverse coefficient problems on quantum graphs. In fact, practically there are no references. Okay, just I can give you probably one, in fact, reference where people tried to develop the method for inverse coefficient problems on quantum graphs. And so we managed to combine together with Sergei Avdonin from the University of Alaska and Kira Khmelnytskaya from the Autonomous University of Querétaro. We managed to combine the leaf peeling method, which invented Avdonin and Kurasov in 2008, which just allows to you, when you solve a problem on a sheaf, for example, this is a sheaf here, you can cut it out, okay, and continue. So you recalculate your spectral data on the smaller graph and continue the process of recovering the potentials on other sheaves and so on up to the end. So we managed to combine this leaf peeling with our approach on Neumann series of Bessel functions. And for example, this is an illustration from that paper where it was, the Weil matrix was given, for example, at 180 points for a quantum graph which consisted of 18 edges. And so this leaf peeling procedure was necessary in this case, and this is more or less the result which was obtained. By the way, here this n was just 9, which in all the cases, which means that just with 9 terms in these partial sums, you obtain this very satisfactory accuracy in this case. So thank you very much for your attention.
Thank you very much for the very nice and interesting talk. Are there
Did you try to use generating function for Legendre polynomials to relate with your series? And then also question about the Mellin technique, Mellin transform. To use representation for Bessel functions, try to use to represent solutions of your equation. I think it could be treated as double Mellin transform. It's related to gamma function series and so on. I think it's some idea what I'm trying.
The generating function here, well, we didn't need it, in fact.
Yeah, you write series with Legendre polynomials, and then it depends on t over x. So we try to make substitution and try to use generating function to relate with your coefficient. I don't know, I just thinking about this idea.
Well, I don't know.
And also t over x, it's some Mellin convolution kernel, so can be Mellin type transforms could be used as well.
T over x is just because in general we work on an arbitrary interval. Okay? So in which sense? For example, we need it for a point x. So we need to obtain our series on the interval from 0 to x. Okay, this is why t over x is just technical stuff. And the Mellin transform, I looked.
Then you introduce, just put Heaviside function and then just extend on half axis and try to use Mellin transform. And because we have some images of Legendre polynomials with exponential functions, some Mellin transform, and play with gamma functions, I see.
You see, here, in fact, what is important is that these spherical Bessel functions, they are very nice, and they possess the orthogonality property from minus infinity to infinity. This was the crucial point. In fact, apart from that, I don't know what more we can introduce here.
Okay, adjust my imagination. When I see Bessel function, I need to attack with this kind of. Thank you. Yeah,
I see. Thank you.
Any other question or comment? Okay, so then let us thank the speaker again.
Thank you.
We have one more talk left, and then we'll be done for today.
Sí, sí, puntero.
Okay, so I will introduce our last speaker of today. Well, what can I say about Daniele? I met him in Kent State. We were both doing our PhD in Kent State. I was a student of Richard Aron and he was a student of Joe Distel. And so we had a great time there, like mathematically speaking. Also with, we met a lot of friends there. We met a really nice group. We made a really nice group, the PhD students, the graduate students. And from there, we just kept being friends, a long friendship that will continues and will continue. And okay, so Daniele will speak about on certain classes of first pair functionals. Go ahead.
Okay. Thank you very much for this introduction, and let me thanks all the organizers for this fantastic conference, fantastic place, and especially I would like to thanks Paco for the invitation. Okay, I'm the last speaker. My position is nice because for sure at the end of my talk nobody asks questions because people want to go for lunch. Okay, let me okay, this is a talk about joint work with one of my students, Jeremy Mirmina. He was first in Catania, but now he moved in Pisa. And let's recall classical definition. Maybe you teach to undergraduate student this definition. If KD is a complete metric space, a function from K to R is called of the first Baire category if you can approximate pointwise on K by a continuous sequence of function. And let's collect the all first Baire category function by B1 of K. Okay, just let's mention the really old result of Baire, that a function is first Baire function if and only if it's a restriction to every closed subset of K as a point of continuity. This is really classic, and also this is another classical corollary. F is B1 of K if and only if is continuous at a dense set of points. Okay, but let's go to Banach space. Okay, suppose X is a separable Banach space. And then we know that the unit ball of its dual, and all with the weak star topology, is compact metriable space. And then it makes sense to consider all continuous function of B of X star. Then we know that X can be isometrically embedded in the C of B of X star. And also the B dual can be embedded in the space, the Banach space of all bound affine function of this ball in the way with the supernorm. Then, since X is in C of Bx star, then one can define B1 of X. It's not like functions, Baire one function in the ball, but we collect all the functionals in the B dual such that there exists a bounded sequence on X, such that X star star can be approximated pointwise on the dual ball by this sequence Xn. And Jean Bourgain, a really young Jean Bourgain, proved that an element in the B dual is in B1 of X if and only if is just a first Baire function. You can approximate by continuous function on the ball. This is just equivalent. That's why the notation B1x or B1 of the ball. This justify the notation. Okay, and finally, let's introduce also the BSC of X, the subclass of we consider difference of bounded semi-continuous function on the unit ball of the dual. This notation, okay, we introduced this notation for some classical result, like X is a reflexive if and only if the B dual can be embedded in the space of a continuous function of the unit ball of the dual. Okay, and also let's recall this classical result, really nice result was proved in the 70 by Odell, Rosenthal, and also Rosenthal, that X does not contain a little one if and only if the B dual coincide with the first Baire one functionals. And also, okay, actually, before the Odell Rosenthal, Bessaga and Perchitsky also proved that the X does not contain C0 if and only if actually if you remember the space of difference bounded semi-continuous function of the ball, unit ball, coincide with continuous function of the unit ball of the dual. This was proved in 1978, really old result. Okay, related to the space, Oscar Rosenthal writes the following question. Okay, suppose we have a functional individual which is first-base functional. And is it also possible to approximate this functional by a point-wise, of course, by a sequence of elements on X, such that the closest span of Xn does not contain a little one? Is it also possible to do that? Or the same, the second question by Rosenthal was it can be if we can do also approximate a one-base functional by a sequence of elements of X, point-wise of course, such that the closest span of Xn has separable dual. Okay, and it's convenient to introduce just notation. We collect B10, the functional in B1 of X, such that the approximation can be made such that the closest span of Xn has separable dual. And we also collect by B11 of X, the functional in B1 of X, first-base functional, such that the approximation can be done by a sequence Xn in X, so that the closest span of Xn does not contain little one. And by the definition, we have this chain of inclusion. That's the lower level, is the space X. Then you go to B10, B11, and of course our definition of B1 of X, the first-base functional, of course individual. And let's see the answer of the Rosenthal question. Actually was positive, was proved also by Bourgain. Bourgain proved that this is true if the functional individual actually stay in this. Is different of bounded semi-continuous function on the unit ball of the dual, still in 1980. And negative in general also was proved by Bourgain in a different paper, still in the same year. Actually, the example Bourgain is really extreme. Extreme in the sense that the example of Bourgain is a Banach space XB such that B10, B11 coincide with the lower level, with the space. And the space of B1 or the first-base function is different, is higher. And let's recall another definition. A Banach space is said to be weakly sequentially complete if X, the B1 of X, coincide with the lower level, with X. And in connection with the above questions, let's recall this theorem, classical theorem. If X is a separable infinite dimensional Banach space, if X has the Schur property, then X is weakly sequentially complete, it has no reflexive subspace. And the second part claims that if X is weakly sequentially complete and has no reflexive subspace, then X is hereditary little one, which means a little one is everywhere in the space. Every infinite dimension subspace contains little one. And then if you consider the Bourgain space I mentioned before, this space also provides an example of Banach space such that the converse of the second part of the part B of the above theorem doesn't hold. Actually, joined with my student, we use the same technique of Bourgain, that we provide another example such that also the converse of the first part of the theorem doesn't hold. The part, in the paper, Bourgain just sketched the construction, but it was really hard to follow. Actually, we try to make the construction with more details. Okay, let's see setting or sequence of Banach space. Actually, we construct by induction a sequence of closed subset of 0, 1 with cardinality the continuous and a sequence of actually the extension operator. Isometric embedding is CK high in C01. For each here, we said that if you fix for each I you fix any closed subspace of CKA, and you fix any sequence in Xi such that with norm 1 which generate the space, you are free to choose any sequence of Banach space Xa, and also in the lower level for I equal to 0, we need this inequality, and also we require that for each I there exists an operator from xi plus 1 to xi which map the element in the level k element in the level I plus 1 to the same, to the corresponding a I k, is such that this operator is strictly singular. Strictly singular means is never in every part in xi plus 1 is an isomorphism. Yeah, anytime you fix infinite dimensional subspace of the xi plus 1, the restriction is not an isomorphism.
The first.
Well, okay, now we are free to choose this sequence of Banach space such that also you have this sequence of associated to this sequence of operator, not strictly single operator. Strictly single operator. And then we consider the element AAK, we consider is remember, AI was just you put inside in C01, and then you consider Fk, the summation of this 1 to the high to Fak, the summation over A. And then consider the closest span of this sequence. What we prove that if every sequence we have chosen, Xi, is weakly sequentially complete, then the space we obtain, X, is also weakly sequentially complete. And in any case, independently how you choose Xi, X you obtain, the space X you obtain in this construction is every time is hereditary little 1. And now, okay, we just choose the sequence. Our sequence of Banach space, okay, here we say yi is just little p with the index I plus 2 over I plus 1. And also, okay, as sequence in this little p, we consider is Schauder basis. Plus, okay, the operator now exists and also is strictly singular because it's a classical theorem that the space little p with another little q is always, they are totally incomparable. That means there is no infinite dimension which is isomorphic to a subspace of little p. And then we are sure that this with the choice of this sequence y high with this kind of little p, okay, we satisfy all the conditions we required before, and then okay, of course, this space generated by this sequence yi is by the previous theorem is hereditary little 1. Of course, each sequence little p is greater than 1. Each space is reflexive and then easily is weakly sequentially complete. And then by the previous theorem, the space we construct is also weakly sequentially complete. Okay, it can be checked that this space is not a sure, doesn't have sure property. Okay, just with, but okay, just we don't prove that. Okay, let's go. Let's come back to Rosenthal questions. Okay, Rosenthal, okay, does it always true that B1x equal to B10 or B1x is also always equal to B11 of x? This, okay, the Spice-Bourgain example, where this extreme situation holds, we construct a new example, actually, but also, to be honest, we used a lot all the ingredient of Bourgain paper. Okay, we construct x equal to space of continuous function in the Cantor set. And at the end, we found out that B10 and B11 actually are never for this x, they are never vector space. And then that means the equality cannot be true. Okay, let's see something. We'll just let's mention the ingredient we use. Okay, a sequence or real value function on a set C, we said that Fn converges strictly on a subset A if this series is pointwise is convergent pointwise on A. Strictly converge. And of course, strictly converge implies pointwise convergence. And let's denote by x b of x star, the set of all extreme points of the unit ball of the dual, and with the weak star topology. And the first, let's introduce also this B1 SC of x. We collect all the functional x star star such that x star star is pointwise living of a sequence xn in x, but such that xn has to be strictly converged on the extreme point of the unit ball of the dual. And what we found out at the end is this new set B1 SC is inside the in B1 0. And also we consider K2 to the omega, the Cantor set. We denote by KRS the system of Canton interval. For a function, if you consider you have a function on the left of this KR1, you can extend to the other part on the right by this small trick. And by induction, we construct a sequence IR and BR of disjoint G delta set in the KR1, and a function phi which is in the classical sense of first Bayer function, such that is 1 is on AR, is -1 on BR, with the sup norm equal to 1. And for each R, you consider just the extension of those phi to the other part on the left, where when t is inside the kr 2 to the r minus 1 and 0 otherwise. And then finally we define capital phi, the summation of 1 over 5 to the r of those phi r arrow, and psi, capital psi, the summation of 1 over 2 to the r of those psi r, which are first Bayer functions, okay? And let's also recall, because we are considering what? We are considering on the Cantor set, we are considering first Bayer function, but this is a small trick. All of those first Bayer function in a classical set can be extended in Bayer 1 functionals in the B-dual. How? Just considering the extension of this Coquet theorem. Just define in the B-dual, because we are working in CK and the dual is the measure space, and just define as function in the B-dual like integral on K of phi on the nu, and this extension is unique, is a classical theorem. And what we found at the end was this extension, those extensions for capital psi, capital phi are such that the capital psi, the functional in the B-dual of capital psi, set in the B1 as C, which is the smallest set. The summation, the sum of phi hat and capital psi hat set inside in B1 0, but at the end, the phi at capital phi is not in B1 1. That means the sum of two elements in B1 0, or of course in B1 1, are not in B1 1. That means those are not vector space. And then it follows that those set for this particular space is contained strictly X, and is contained strictly in B1 of X is also an example. But we managed this space, which was much easier to describe a family of Banach space. Okay, let's recall that classical Banach-Mazur theorem, that every several Banach space is isometrically embedded in C to the omega. And we consider F C to the omega, the set of all closed subset of C to the omega, and we keep this set of closed subset, the family of those closed subset, by the Efros-Borel structure, which we consider in some sense the open set are generated by an open set in C to the omega by this condition. We collect all the clauses which touch this open, fixed open. And we denote by S of B the subset of this family of closed subset of C to the omega, consisting of all linear closed subspace of C to the omega with the relative Efros-Borel sigma algebra. And Bossard in 2002 proved that this SB is a Borel subset of F of C to the omega. And then, okay, since this Bossard theorem, anytime you have a property for a separable Banach space, you can study like the script set family. In the script set theory, you can describe if this family, this property is a Borel or not, or is analytic set, and so on. Actually, using this, this family, we proved that the family of all separable Banach space such that the inclusion is strict. Inclusion between B11 and B1, but the same B10, B1. When it's restricted, this is not Borel. Actually, we proved this family is sigma 11 hard. Those properties in particular implies those are not Borel. That means the Bourgain example, as well as the example we presented also, we introduced it, are not isolated. That means since this family is not Borel, that means you have a lot of several Banach space with such a property. And okay, maybe I don't have so much time, but let me also ask this question before we leave. But we don't know if there exists X separable Banach space such that B10 is strictly contained in B11. That means what? That means anytime you approximate an element here, a functional, with a sequence, that means X star, remember, that means exists Xn in X such that the limit of Xn of X star equal to X star of X. For any X star, let's say the unit ball. Okay, it's such that the span, closed span of Xn does not contain little one. Is it possible to approximate this? Okay, I don't know. Is it possible to approximate a functional with a sequence such that the closed span of Xn does not contain little one, but anytime you approximate with any sequence on X, this closed span as separable to one. Actually, there is work by Ted Odell, which is related but does not answer this question. But I don't know the answer. And thank you very much for your attention.
Okay, thank you very much. Very strong results, a very interesting question. Does anybody have a question, remark, comment?
Okay, my conjecture was false.
Okay, so I think your results are just for separable Banach space, right?
Yeah, for sure.
Yeah, because you need the metrizable
Separable
space.
because you need that the unit ball of the dual is metrizable.
Yeah, so do you think is there a way to generalize the sequence convergence to a certain cardinality?
Actually, people was done by, was a paper in the 80s by Richard Haydn, maybe Odell, and maybe Rosenthal. People already studied this kind of question when the Banach space is not separable.
Okay, so
you already have. Yeah,
okay,
I can give you the reference.
Okay. Okay, and also, is this B10 dense in B1x?
Sorry, B10?
Yeah, B10 of x. Is this dense in B1x? Or?
That's,
because, yeah, I think you want to say
actually,
it's a subset, a proper subset.
Yeah,
is it dense?
That's, let's say, but actually I don't know. Yeah, I don't know, because you require that anytime you require that the span, closed span of Xn, you consider the dual is separable. And to be dense, to check the density.
Yeah, whether the closed linear span, because you say, because what you proved,
Okay.
I think the example you gave is not a subspace or something.
Actually, okay, you have density because you have this one, no? And you have density from here to here, and then you should.
No, X is just weak star dense, right?
Sorry?
X is just weak star dense, but not.
Yeah. You ask me, okay, dense in norm.
Yeah, of course, you are not saying weak star density, there's no.
I don't know. Okay, because I was thinking about always considering weak star topology.
Yeah, because your counterexample just shows that it's not even a subspace, something like that.
Yeah.
So if you take the linear span or
I don't know
something.
the answer. Okay, I don't know.
Okay.
Maybe I never thought about this question.
Okay, thank you.
Any other question? Okay, so let us thank the speaker again. So actually we have lunch now in la taberna La Cigarrera. We'll send you the link through the WhatsApp group. Thank you.
Matrix, debe ser, ¿no?
Vale, Jesús, dale al ordenador, porfa, el audio.
Ya tienes.
Acércate a un micro y habla, por favor.
Me está entrando una demo.
Hola, hola. Hola, 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 hola.
Mira, hola, hola, hola.
Vale, por algún motivo que yo no entiendo, este ordenador genera bucle.
Escucha,
¿Qué es lo que necesitan ustedes?
Probar para que mañana se escuche a los ponentes de fuera, se les escuche.
Ya, vale. No hace falta que me quede yo.
No, no hay problema. No te preocupes, es que necesitamos probarlo porque mañana no sabemos siquiera todavía quién viene. Porque a María se ha ido mal, la urgencia.
La
Vamos bien.
última, a ver, la única, mañana solo hay una charla online, que la speaker es online.
No, pero eso está encendido eso. Ah, vale.
Y es,
Se le quita,
es la última.
el audio ahí, ¿no?
Es la última, a la 1:30.
¿Qué audio?
Vale.
Esto bájalo a tope. Un momentito, ¿eh?
Vale.
Hola, hola. Hola, hola, hola. Claro, se escucharía. O sea, que no se escucharía la gente.
Espérate, Enrique, vamos a probar aquí.
Pero podemos poner un ordenador ahí.
Probando.
Hola, hola.
Jesús, prueba por favor a subir el volumen al portátil.
Está puesto, ¿eh? Dale ahora. Más, sí.
Enrique, habla.
Ay, ahora me sacas de la cámara.
¿Tienes el
Hola.
micro?
Hola, hola. ¿Qué tal? ¿Cómo estáis?
No se escucha aquí.
No se escucha, ¿no?
Es que debería de escucharse aquí en el auditorio y no se escucha.
Yo lo tengo abierto.
Espérate, Enrique. Es que mira, ¿eh? Prueba otra vez. ¿Habla otra vez?
¿Me meto otra vez?
Sí, habla. Pero no te salga, hijo. Si vamos a probar.
Estoy probando porque no sé si es del mismo YouTube o qué.
¿Que YouTube?
Hola, hola.
Vale.
Si tú le bajas ahí.
Habla.
Hola.
Y ya está.
¿Qué te está entrando? A ver, tú sales de la fila. Hola, hola. Probando, probando. Bájale el volumen, Noemí. De ahí, de ahí. Hola, hola, ¿qué tal, qué tal, qué tal? Bájale un poquito. Así, así. Yo lo dejaría. Súbele un poquito más. Un poquito más, Noemí. Hola, 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 hola. Hola, hola. Bien, aquí estamos por la tarde, tal, pues. Hay un poquito de eco. Tú sabes,
Bien,
tú sabes.
aceptable. Vale, ¿qué pasa? Javi, esto te incumbe a ti.
Más
Eso
cositas.
es para que el ponente para escuchar los micros de aquí. Claro,
¿Qué se escucha ahí?
importante. En el momento en el que se coloque este micro, no sabemos si se va a volver a hacer el bucle. Por lo cual, hay que estar todo el tiempo. Habla el ponente. Te doy.
Ya cortamos
El ponente va a responder una pregunta. Muteamos.
Mutea.